from Alma Butter team, and I'm here to present to you our masterclass on mastering Netflix personalized recommendation strategies. But before we go ahead with this interesting masterclass, let me give you a little brief about Alma Butter. So we are a student first edtech platform, and we relentlessly work towards a better tomorrow for our students. So in today's masterclass, you will be learning about explore how Netflix uses advanced techniques for personalized recommendations. Second, understand algorithms driving content strategy suggestions and user engagement. Third, learn how data insights and feedback enhance recommendations and the viewer experience. Fourth, discover the impact of personalized content on engagement and satisfaction. And last, dive into upcoming trends for personalized content curation on Netflix. So now I will introduce you to our esteemed instructor for today, who is a data engineer at Mercedes-Benz Research and Development of India, Mr. Avinash Singh, who will bring his technical expertise about Netflix advanced techniques. He himself is a data enthusiast and he comes from West Bengal. I will now hand over this session to Avinash. I hope you have an amazing and stimulating learning experience through this masterclass. Over to you, Avinash.
Thank you, Ranjana, for your introduction and for bringing me to this platform to connect with a wonderful community. So, a very good morning to one and everyone present here in the call. I hope you're having a good day, right? So, just let me give some basic idea about what are we going to discuss today in the call. So, before that, introducing myself, I am currently a data engineer at Mercedes-Benz, and yes, as Ranjana mentioned, we are going to discuss something about recommendation system, right? Yeah, am I audible?
Yes, you are.
Yeah, sorry. So before I begin presentations, before I start any formal talks, I would love to know, my audience here. So there are a few questions from my end, from the audience. I want this session to be very interactive, right? So it will be like, two directional conversations, bi-directional conversations. So to begin with, my very first question to everyone here, like, how's your mood today morning? Let's be very interactive, we can have a friendly discussion. I would like to know your mindset right now, how much you're prepared for this session. Energy is high or low. So can you just ping it on the chat section? How are you feeling today? Come on, I'm waiting for your messages. We have 9 attendees in the call right now. Okay. High energy, exciting. That's good. That gives you more motivation, right? When the audience is energetic, I will be really excited, to do the knowledge transfer. Sounds good. So let me just start presenting my screen, right? And one more question, second question. I would like to know your background. Like, how many of you are from a BTech background or MTech background, BCA, MCA, or any other subjects, in graduations? So that will help me to understand my audience, and I can deliver my discussion accordingly. The seminar can go on in that direction. So please let me also know your background. So Raghav Moore is from BTech. That's good. Any other? Abhishek is from BTech. Please mention your department also, right? So if it is BTech CS, mechanical. Okay, BTech IT. That's wonderful. So Abhishek and Raghav are more interactive. So yeah, so they're like my buddies. All right. So I'm assuming the crowd is basically from BTech as well as some computer applications background also. That makes things more easy for me to begin with. So let me just start sharing my screen and let me know please if it is visible.
Yes, it is visible.
Thank you. So the introduction to Alma Better is already covered. So yeah, I would start with my segment. So this is what we are going to discuss today. The title would be Mastering Netflix's Personalized Recommendation Strategies. Uh, Disclaimer, we are not going to only cover about Netflix as a whole. we are also going to focus on actually what is a recommendation system, be it any platforms, right? Starting with the social network, you have Facebook, Insta, Snapchat, you have YouTube, you have Netflix, Amazon, Flipkart. All these platforms use recommendation systems in their own way, right? So how this recommendation system impacts the business, how are basically algorithms developed? We will first create a foundation to the recommendation system, and then we will slowly move on to what Netflix is actually doing, right? So a short introduction about myself. I am Avinash. My background, I have basically completed my MTech in mathematics and computing from IIT Patna, following which I was an intern in the R&D department in Novartis Healthcare, where I was basically in one of their deep learning projects. And finally, I joined Mercedes Benz, where I am basically contributing as a data engineer. So I have, a mixture of data science and data engineering experiences. I'm still learning a lot. There is no limit to learning, right? So as I always say, uh, our best is always nothing, right? So we always have to keep on improving and learning. So starting with today's agenda, so we are going to start with leveraging graph network analysis for personalized recommendation. So we are basically going to focus on how Facebook is actually giving us friend suggestion. That's the very fundamental problem statement we are going to solve, right? After that, we are going to see why social media and recommendation system is actually important in the business. Following that, we will understand social graphs. So basically, the objective will be to first of all solve this problem statement of Facebook recommendation system using graph networks. So you will see how graph network can basically help us to get friend recommendation. We'll discuss more stuff about friend suggestion systems, the ego network, neural network. We will discuss word embedding and node embedding. That is the heart of this graph networks, right? And finally, we will switch to content recommendation, which is about Netflix, how they use collaborative filtering, the Netflix problem, and the small mathematics behind it that has actually done a lot for Netflix, right? So yeah, without that's too much of introduction. Without further delay, let me just begin the presentation. So I hope every one of you is ready. Let me just see if there's any Q&A. It's okay. Fine. Oh, so you can just see this image in front of your screen, right? So just let me know what is the conclusion you derive once you look at this image. Please be very quick in the chat section. I want this to be very interactive. What is the conclusion when you look at this image? Waiting for your responses. Abhishek, Raghav. Chat is not very connected graphs tree which connects to top. Sushil says chat is not enabled. So please, the team, please look into this. Okay, connected graph trees which connects to the top. Somehow that is true. This is the image of a very complex network, right? Assuming this to be a Facebook network, right? You can see how people over the world are connected with each other. I'm assuming these small nodes. Let me just use the laser pointer. In case you find any trouble, please let me know. These nodes may be your users, right? Like me and all the guys in the call, and there are lots of people on Facebook having an account. These nodes can represent that particular node entity, right? The users of the Facebook, and the edge between them can indicate whether this particular person here is connected with this particular person on Facebook, right? Likewise, there are millions of people and millions of users on Facebook, and you can see the complex network that has evolved through time, right? Even right now, I'm giving the session, there might be some friend requests being accepted, right? And lots of edges being created. So the graph keeps on growing and evolving. The problem is we need to now figure out how can this particular structure of the graph be used to enhance the performance of the recommendation systems, okay, and increase the customer satisfaction. That's the topic. We will be leveraging the graph network analysis for personalized recommendation in social media. So a brief idea about why social media is actually required. Lots of us have lots of social media accounts on our phone. The question is, why do we actually need social media? We are all aware of that, right? We need for global connectivity, connecting people from one place to another in the globe. Professional networking, obviously, LinkedIn is a good professional platform. We need to connect networks. Content sharing, obviously, we are sharing contents on Instagram and lots of other social media. Real-time updates, anything going around the world, we are able to know, right? What is going around. Community building is an important, we have seen right now what happens is people building a developers community, travelers community, blogging community. All these are different types of community being built on social media, and influence culture, obviously, like the bloggings that they do. That that basically influences the crowd, right? So these are the different reasons why one likes to be a part of social media, right? Now, why actually is the personalized recommendation system important? Is the title visible? Should I hide this? Let's see. Okay. So the question is why personalized recommendation is actually important. The very first thing, tailoring content delivery, right? So users will be more likely to engage with the content that is basically satisfying to them. You as a user, right? You are a computer science graduate. You will be more interested to see the content related to computer science technologies, right? You have no interest in, suppose going through the content which focuses on, suppose what would I say? Suppose health fitness, right? You don't have any interest in health fitness. You're not actually interested to look into contents about that. What if every morning you open your Instagram and you get contents related to health fitness? You'd be very annoyed, right? So you want to see only those stuff which you are actually interested in. So tailoring content delivery is one of the challenge that the recommendation system should solve. They will give you the recommendation to only those content which actually you are interested in. Time efficiency is important, right? I'll open the I got a chat. Okay. So time efficiency is important, right? Users don't want to waste their time just looking for the content they want. I'll open the Instagram. I want the post which I actually love to watch. If I don't get that, I'll just switch off the Instagram and move on. Retaining the customer is very important. You don't have much time. You will get hardly 10 seconds to retain a customer. This is how the business works. You'll not get more than 10 seconds to retain the customers. If a customer comes in your platform, suppose Amazon or Flipkart or Instagram, if they are annoyed in those 10 seconds, they will not come back again. And if you lose your customers, you've lost to the business. Platform loyalty, obviously, you are satisfying the customers. Your recommendation engine gives all the posts which are relevant. You are enjoying the content, and that basically builds the platform loyalty. You will suggest your friends also, come on, you can come on Instagram, follow this group. It's very interesting. Cross promotion, obviously, wherever there is a crowd, companies and businesses try to promote their products and according to your need, right? If you're a singer, obviously they will suggest some high tech microphones, all the stuffs. If you're techies, all the tech gadgets will be recommended as an advertisement. So based on your interaction with your social media account, these things are recommended. And obviously the last, this guy, generating revenue, right? That's the sole part of this problem statement. Solving this problem statement, more customers on your platform, more advertisements, more business going on, and obviously you take home a lot of money. That's the challenge we have to solve. Let's understand social graphs, right? First, because we are going to solve this problem of Facebook recommendation. So let's understand what actually is a graph network. So if you look at this image in the right, each node actually represents a user in the social media, right? Suppose example, we'll be discussing about Facebook. So each of these nodes can represent a user having a Facebook account, right? And two nodes will be connected with each other if though those are friends of each other, right? That's how the network is built. You are a user, I'm connected to you, that means I have added you as a friend, then we both will be accepting the friend request and we will be connected. That means there will be an edge between us, right? The question is, does the node always belong to users? It's no. The nodes can be users, the nodes can be the Facebook groups, the nodes can be the Facebook post or the content which is being delivered continuously in Facebook, and the nodes can be the post which you have liked. So suppose if this is me and I have liked a particular post, then there will be an edge between me and the post saying that I have liked this post. That particular thing can be also captured in terms of graph, right? So this was about nodes and edges, right? How social media, how we can represent the entire network in terms of nodes and edges. Let's understand the social graphs. I would love to hide it. All right. So let's understand the social graphs. So suppose we have two social platforms. One is Twitter and one is Facebook, right? This ABC has an account on Twitter. ABC here, separate ABCs have account on Facebook, right? So if A follows B, A follows B, then it is not always true that B will also follow A, right? So if I am following SRK, obviously it's not obvious that SRK will follow me back, right? So this is a one directional edge. So this is a directed edges. We see this kind of edge also available in Twitter. But if B follows me back, then it will become an undirected edge. So what are the different types of edges possible? A directed edge from A to B, okay, and a directed edge from B to C, which means B is following C, and A is following B. We can have an undirected edge. For example, in Facebook, if I send a friend request to B, then B will be accepting the friend request, right? And automatically there will be an edge between A and B, which means A is the friend of B and B is the friend of A, right? So there is no point of giving direction because it is a two-directional friendship. I follow B and B also follows me, so it is an undirected edge. So these are the different types of edges which we'll see in the network graph. Now, having laid the foundation about what the graph is, how does it look, what are the nodes, what are the edges, we can solve the problem of friend suggestions, right? So you might have seen when you open your Facebook, we get suggestions like this, right? That people you may know. I'm not connected to these people, but I actually get recommendations that you may know these people. How is it helpful? So maybe in school days, I had a very good friend, but after I moved to high school and college, I got disconnected with him. I don't have his number. I'm completely disconnected. But somehow down the lane, after 5 years or 6 years, I get his name in my suggestion. Don't you think that is exciting? Because he was my good friend. I was not connected with him. But now if I get his suggestion, I immediately connect with him. And that's how we can continue our friendship, right? So this is a very cool feature of Facebook, recommending your friends, right? How does it do that? Let's understand it in detail. The very basic concept is ego network. This is a user in the Facebook, right? This particular user in the Facebook has an account, and these other nodes also are users on Facebook. Now, what are the different types of nodes present in his network, right? That means what are the different types of folks he's connected to? First of all, his school friends, right? He can have his school friends. In his school, he has a lot of friends. So those are connected with him. So he's connected with all of his school friends, right? He's also connected with all of his high school friends. He's connected with all of his college friends. He's connected with his family members. So you can see the family members, the high school friends, the college friends, and even his department friends are the part of his social media network. They are the part of his social media network. First thing, what are the different types of communities that have evolved? Obviously, his family members will again be connected with each other. If I am connected with my father's Facebook account, my father is connected with my uncle's account, mother's account, my siblings account. So you can see a small network within that also, right? This is a cluster. Family members connected with each other. Secondly, high school friends. I'm connected with most of the high school friends. Those high school friends can also be connected with each other, right? That is another community. Similarly goes for college friends. So you can see the graph basically makes it very easy to visualize the network that I am actually working on. So this is the ego you. What does actually ego means? The owner of the network. So if I talk about myself, this is I am the ego network, which means this is my ego network. So I have the friends from different segments, from schools, colleges, high schools, as well as family members. And this is how they are connected with each other. How is this going to help us to get this suggestion? Graph neural network, right? So we understood what a graph is, what basically are the components of a graph, what our ego network is. Now we will discuss the graph neural network, which will basically help us to solve the problem. So graph neural network is a type of neural network which will directly operate on the graph structure. So, okay, so I would like to know from the audience if you have any idea about the neural network, right? So this neural network is a very core part of artificial intelligence. You have a neural network, a model which is capable of learning stuffs, right? So keeping the neural network in a black box, I would say you have the graph structure in front of you, the network which I showed. Suppose this one, this is a graph structure, right? And you have a very intelligent model sitting on top of it, which is basically capable of figuring out the dependencies and the relations between different users, right? How is he connected with each other, whether they had same school, whether they are from the same family. Those stuffs can be captured by a very smart model, which is the neural network. Now, how does this is going to help? So the core of neural network is basically the node embedding, right? That is important. I will discuss about node embedding. Now we are going to switch to NLP. Right now we are in graph neural network. So graph neural network basically means graph plus neural network. So you found out the dependencies, you have the graph with you. Now you have a very smart and intelligent neural network, which is capable of finding relationship between them, get some pattern, and that will basically help you in recommendation. But before that, there is an intermediary step, NLP, natural language processing. We have to find the node embedding. How do we do that? So we will dive deeper into understanding what word embedding is all about. As I told, this session, we are not only going to understand recommendation, but also different components of machine learning and AI and deep learning that is going to basically contribute to recommendation system. So, so far so good from the audience. I just want a quick yes, no. Any challenge, any problem in understanding this so far? Because that is basically how I'm going to direct my slides. So far, the discussion about graphs and the neural networks, is it clear? I'm waiting for your response. Any comments? Okay, I can see some chat. Clear for graph and network. That's cool. Thank you. So please confirm. I want this to be a bi-directional conversation. It's not that I'm just going to present the slides. Until and unless you enjoy it, you understand it, it's useless for me, right? Okay. So understanding the word embeddings now. As I told, I have the network with me. Now each node is connected with each other nodes, right? Before that, let's understand what word embedding actually is. Look into this figure properly. I have three words in front of me: the king, the man, and the woman, right? Assuming I'm defining each of them on the basis of some features. For example, what is the gender? Okay, how much wealth he has, how much power he has, what is the status in the society. Suppose these are the four features on the basis of which I'm going to define this king. Okay, and this color code is on the scale of 0 to 1. So if it is 1, it will be white, and accordingly, based on the values, the color is going to change, right? So color is supposed between 0 to 1. If you look at king, you have some specific color features, right? So this has some values, and for that values, they have got some colors. Look at the man. It also has some colors for each values. I told you, right? The very first feature is about the gender. Second is about, suppose, about the power. Third is about the wealth, and fourth is about the status, right? These are the four parameters on the basis of which I'm going to define king. Now, what is the difference between a king and a man? What is the difference between a king and an ordinary man? On the basis of, suppose, gender. Suppose this is the gender feature, okay? The gender will be same, right? He's also a male, he's also a male. That's one feature. You can see similar column, right? He's a human, he's a human. Suppose this is also a feature. That's very vague features to be considered, but there are similarities between a king and a man, right? To certain level. And there are some dissimilarities also. The dissimilarities is in terms of wealth. King is very rich, and the status in the society. King lies on the top, right? So two features differentiate a king from the man, but the other features are very similar for a king and a man, right? Similarly, for a woman and a man, what is the difference between a man and a woman? So difference between man and a woman, obviously the gender's perspective, right? Otherwise, they are very similar, right? Nowadays, even there's no difference between the male and the female, right? They are very much similar. So only the gender part comes in. That feature actually is a differentiating factor between a man and a woman. So if I can define a man with this color code and I can define a woman with this color code, what is the point of difference? One point of difference in terms of one feature. You can see maybe the gender. Man is a male, woman we call for females, right? That is the segment. So we can see how man and woman is different. So they have a different color codes. They are almost similar in terms of color coding. Only for one feature they are different. That is the gender part. This is how basically we are going to visualize how does the computer or the models understand words. They will understand words in terms of numbers, right? And how do we calculate those numbers? Towards my right, I have a person called Jay. Okay, I have a person called Jay. Now let me take better somebody from the call. Okay, suppose Abhishek. Suppose this is Abhishek. I'm going to define Abhishek on the basis of two features. Okay, so no offense. I'm not going to take Abhishek. Let me take Jay itself, right? So I'm going to define Jay in the terms of two features. The first feature is going to be his IQ. The second feature is going to be his EQ. Okay, so I'll say Jay has a very low IQ of minus 0.4 and Jay has a very good EQ of 0.8, emotional quotient, right? Similarly, there's another person, one, I'll say has an IQ of minus 0.3, again low, and an EQ of 0.2. There is another person in the room, person two, who has an IQ of minus 0.5 and EQ of minus 0.4. So what is IQ and EQ? This is my trait, suppose the features. Now, if you plot this into, now this can be considered as a coordinate, right? Two-dimensional coordinate, because I have two features, I'll be plotting them in a two-dimensional plane, XY plane. If I plot this point, you can see J has a vector here. Person 1, minus 0.3, 0.2, if you plot in this two-dimensional graph, having a range minus 1 to 1 and minus 1 to 1, You can see person one has an edge in this direction, the vector in this direction. Based on this value, person two has a vector in this direction. Now, what's the point of interest? J and the person one somehow are very close to each other, but J and the person two are not that very close to each other, right? So you can see J has an IQ of minus zero point 0.4, person two has an IQ of minus zero point 0.5, quite close. But there's one feature on the basis of which they're completely different. J has an IQ of zero point 0.8, but person two has an EQ of minus zero point 0.4, completely different, ways apart. That's why we can see their vectors are very way apart, which means there is no similarity between J and person two. What about J and person one? J has minus zero point 0.4 and person one has minus zero point 0.3, very close. Trait 2, J has zero point 0.8, this has zero point 0.2. Pretty close, not that close, but still they are very close. So that's why we can see the vector of J is very close to the vector of person one. So if I'm representing a person in a vector space, that means a two-dimensional space. Vector space is nothing but n-dimensional space. If I'm taking two features, I'm going to represent that user in a two-dimensional space. If I'm taking three features, IQ, EQ, and health fitness, maybe third feature, I'll be representing them in a three-dimensional place. Consider four features, a four-dimensional space, n number of features, n-dimensional space. The idea is if there is similarity between the features, they will be lying very close to each other in the vector space. That's it, right? Now, visualizing it is fine, right? But how do we visualize them in an n-dimensional space, whether they are very close to each other or not? There comes the concept of cosine similarity of vectors, very fundamental concept, right? So this feature can be considered as a vector of J. How do I represent J? J is represented by a vector. I repeat again, J will be represented by a vector. Person one, person two again represented by a vector. If I want to find the similarity between J and person one, I'm going to find the vector dot product, right? The cosine similarity. How do you find the angle between two vectors, right? The cosine similarity will help you find the angle between this vector and this vector. Here I have taken two features, assuming in the bottom left here, I have taken five features. So this will be basically in a five-dimensional space. You cannot visualize it right now. That's why suppose we are going to find out the similarity between them. How much close are they? So I have represented J by five features, similarly for person one and person two. Now looking at this, I cannot directly conclude whether they are very close to each other or not. Close means are they very having very similar attitude or features, right? So better find the cosine similarity. Vector this dot vector this. So when I do the vector product of J and person one, I get a value of 0.66. Similarly, for J and person two, I get a value of minus 0.37. Very different. Which one is very close? Obviously 0.66, and it was obvious, right? When we saw the values of J and person one, they have very similar features, and we can say J and person one can have a similar mentality, similar hobbies and all those stuffs, right? And similar IQ, EQ, all those stuffs. So this is how a word is represented in terms of a vector space. This will be the very fundamental thing that we'll be using in graph convolution network word embeddings. First start with word embedding. How does the model understand what a word actually is, right? So we have to convert the word into vectors. How do we vectorize? We got it, right? Maybe I think there's a chat. How do we get or learn this embedding? Yes. So there's a separate model, word to vec. There are lots of training methods. How do we train this embedding? So that's a good question. How do I find out whether J has these features? There's a huge corpus with us, right? Huge text, billions of text. So like if you look into Google's what to vec today after this session, you just look into this, how Google what to vec was trained. So they had used the news headlines, newspapers, content, all those stuffs where the complete text corpus was crawled, and the model learns the context, right? If I say, today I will go to the bank to deposit money. Today I'll go to the bank to deposit money, right? So here I've used the word bank. And the next line, suppose I want to say that I enjoy sitting beside the river bank. So bank and bank, synonyms, right? They have similar names, but the meaning is different. How do the model understand the difference between the first bank and the second bank? The first is the bank institution where we transfer money or withdraw money. The second is the river bank. How will the model understand this? So when you're training your what to vec model, we understand the context. So it will not only focus on the word bank, it will also focus on the words before the bank and after the bank also, maybe, right? So that it understands the context, the words around it, which is being actually used in the sentence to figure out if it finds the word money also, if it finds the work transactions or deposits, withdrawal. Those words will give you an idea that, okay, I'm referring to a bank, which is a financial institution. the bank where we do transactions. And in the second sentence, where I said, I am sitting along the bank, I'm sitting along the river bank, the river and bank, different thing. So this is not a financial institution. Obviously, this is going to be a river bank. So this is altogether a new concept, a separate concept about how what to wake is trained. But for your to your answer, so the solution is they have text context, the text corpus, they take into account the context of the word embeddings, right? They take into account the context of the words, in which context is the word is being used, what is the word before it, after it, the n-gram stuffs and all, and finally they come up with a word to wake model, right? So there's a separate paper on this. Please refer to that, because that is again going to be a big discussion. But obviously the context matters. The context has to be captured when we do training the embedding, right? So I hope that answers your question. Moving to the next slide. Once we are aware about how the word embeddings are generated, right? Now we can represent any people and things as vector of numbers. This was the main part, right? We can represent any person or any words which you have as a vector of numbers, right? And the length of the vector can be user defined. We want only three features, so n equal to 3. If you want n equal to 50, n equal to 300, that's up upon us. How many features are there on the basis of which you want to define that word? And we can use that similar vector. We can calculate how similar are the vectors to each other. Just now we calculated how similar are the person 1 and person 2 to each other. Fine. So assuming now the king is defined on the basis of 50 features. Suppose this is a 50 features, right? On the basis of which king, man, and woman are defined, right? So as I told previously, also in the previous slide, the pattern between king and man is very similar, except some basic places. In terms of the status in the society, king is on the top, right? Man is an ordinary man. In terms of power and wealth, those features, the king and the man, the color codes can be completely different, assuming these color codes are nothing but values, right? So in within some range. So the king and the man are very similar in many respects, but in some key respects, for example, in terms of status, wealth, power, army, they will be different. So on that places, you can see the color codes will be different. And similarly for women and men, they are similar in some terms, in terms of gender and other factors, maybe they will be different. So there is a very slight difference between a man and a woman embedding. What is interesting is how it is capturing the context also. So if I have a king represented by these 50 values, these 50 numeric values represent a king, right? I have a separate 50 values to represent the man, and I have a separate 50 value to represent the woman also, right? So I have a king, I have man, I have woman, all represented by vectors. 50, suppose a dimension is 50. So in 50 dimensional space, I have represented a king, a man, and a woman. Now, if I do the subtraction of king minus man, so from king, if you remove all the features of an ordinary man, so from a king, all the features, suppose, of the ordinary man is removed and the features of the woman is added, what are you going to get? Obviously the features of the queen. Why? Because you're removing the male part and adding the female part. The only thing is the gender may be different, because the man is the king has all the power, all the supremacy, but the male component is removed. Now the vector of woman is being added. So the power of a king plus a woman, she will become a queen, right? She will obviously become a queen. So that's basically the idea of showing when you're representing these words in terms of vectors, it also takes into account the context. So because it has been trained on context, right? So the context is also being captured. So if you're subtracting the vector king with man, minus king minus man, and that vector, what you get, the values, 50 values. If you add again the values of woman, vector addition, you'll get a vector which will be very close to queen. So this was the color code for king, man, woman. If I remove this man part from the king and add the woman part, you're going to get this feature. These are the values you're going to get. And this already we know is for a queen. Now you will find out there's a very similarity between king minus man plus woman and a queen. The color codes are very, very similar, right? Only slight difference, but they are very close, which means in the vector space, in the 50 dimensional vector space, if I have 50 features, when you represent king, man, woman, king minus man plus woman, and queen, you'll find out that this particular point will be very close to this point. So the angle between this vector and this vector will be very less, because they are very close. You can see they're almost very similar, right? So this is how we see embedding in the vector space. I hope that's so far so good, right? So any response from the audience? I hope it's good so far. You understood how the words are basically visualized in the vector space, right? Now coming to the graph representation part. how now we found out the embeddings of the nodes, right? We found out the embeddings of the, okay, a response from the crowd. Cool. Rajesh is fine. So he's comfortable with whatever we have discussed. I hope the same applies for all. Since we know now, how do we convert these features into embeddings, right? Now we will see how do we convert a node into node embedding, right? So, okay, good morning, Camilla. So now we are going to find out how do we convert a node into node embedding. Now, if I am a user of Facebook, I have my Facebook network. What are the features in my profile? First of all, I will have a user ID. Second, I will have information about what I am doing. Like where I am working, what was my school, where was my high school, which is the place for my which I belong to. These are going to be the features of a node. Agree? Yes, no? These are going to be the features of your nodes, right? Uh, Goal in sense reinforcement learning. So can you please clarify the question, Aradhana? Okay, fine. No, goal in the sense for this slide, you can see what is the target of having this particular discussion. So the idea is we are going to represent a node in terms of a embedding vector space. Okay, that is the goal. So we are not doing reinforcement learning as of now here. Goal can not always be reinforcement learning. We have lots of other goals also. For example, right now my objective is, since I know how to define a word in a vector space, now I want to know how do I define myself, a user, in the entire network space, in the network space. So the task, the idea is for machine learning is the node has to be converted to a vector. This is the network. This is the user connected to this user. This user is further connected to these users. How do I convert this network, this user, to a vector? This is my sole objective. Now, so this is the suppose graph network. It can be any network, suppose a social Facebook network only. The idea is how do we visualize this in the two-dimensional plane? There are algorithms which basically helps you to visualize this in two-dimensional plane, and we can see the network, the nodes which are similar color, when you're plotting it in a vector space, they are very close to each other, right? Except some edge cases. The greens are very close. These may be outliers. The blue nodes are very close. The purple nodes are very close to each other. So this is the idea. How do I visualize the nodes, which is suppose uh, from the call, if I take Abhishek, right? So Abhishek is a user, Rajesh is a user, Raghav is a user. So these three can be connected to each other. Suppose here, they are a part of Alma Better. They do classes together. So they can be represented in the network. They are connected with each other. How do I represent them in the vector space? So I have to convert them into a vector. First objective. The network is defined. I know how the network looks like. How do I convert each of them into a vector? And what are the features that I should take into account when I'm converting them into a vector? Obviously, basic features are important. What is the ID? The gender, some cases yes, some cases no. Demography information, the geographic location, where do they come from? Their high school information, where do they study? What do they do? What are the pages they follow? What are their interests? What are their hobbies? All these are features. These features will be used to create a vector out of the user, right? Uh, Education, job interest, obviously. So if you're following Alma Better, maybe. So the algorithm is very smart enough to figure out you have something to do with education and upskilling. So if you have similar interests, again, in the vector space, you will be lying very close to each other. If I assume this is the network of the guys here in Alma Better, whoever is joining the call, somewhere they have a similarity of interest, right? Somewhere their age is similar, quite similar. They have similar education background, BTech, engineering, computations. Interests is same, hobbies might be same, and based on that, you can see they will be very, very close to each other in the embedding space. When we visualize them in a vector space, they will lie very close to each other because there are lots of similarities between them in terms of the features which I have considered. Their geography, the courses that they follow, the pages they follow, what are the interest, what do they want to do, and all those stuffs. So now, how do basically we? Uh, okay, fine. So how do we represent the graph now? Okay, question is, are we only interested in taking the user's personal features for recommendation? No. Why? We know a man is known by the company he keeps, right? It's a very common proverb in English. A man is known by the company he keeps. So your interest, your personality, your identity will also be defined not only by your personal features, but also by your company, right? Who are in your network? Whom do you interact with? Whom do you always hang around with? Those the features and of those guys are also going to influence your personal vector space, embedding a representation in the vector space, right? Are embeddings done in context wise? Is there embeddings related to word embedding search? So I am just that's what Kamala we are going to discuss. Yes. So here that embedding that we are going to use starts from the word embedding. So suppose your interest is computer science. So computer science is a word, right? Computer science is a word. It will be having a specific embedding for it, right? So computer science plus suppose I'm going to take example of Camilla herself. Okay, Camilla only. So Camilla is a computer science student. First feature, suppose from Bengaluru. Second feature, background is BTech. Hobbies are AI/ML, maybe uh, follows Alma Better. Suppose I took 5 features. These 5 features are nothing but words, right? 5 words. So you convert these words into embeddings. Okay. You convert these words into embeddings. So all these 5 features are converted into embeddings. We aggregate them. Vector addition. I showed you, right? King minus man plus queen. Whenever we do vector addition, the context get captured. So all the 5 features of Camilla are going to be aggregated and we get one vector, single vector that will basically capture all the properties that I have basically been using to describe Camilla. The 5 features gathered when you do the vector addition, you get a single vector representation that is basically going to represent Camilla. Similarly, if I take another person from the call, maybe Abhishek, same features. Abhishek is BTech background, computer science student from Karnataka, or maybe he's from Hyderabad, follows Alma Better, interested in ML. These 5 features will have a separate vector representation. Aggregate them, you get a single vector again after addition. Now the vector of Abhishek and Camilla will be very close, not that close because of location, maybe there will be slight difference, but still they will be very similar to each other. The cosine similarity, when you find out these vectors, they'll be very similar to each other. So this is how basically the informations are basically being used to represent the vectors. So we store features in some vectors. A vector stores multiple labels as assigned one line. Yeah. So the tags that we are going to use, those are converted to vectors. We aggregate them to get a single vector. That will be the vector of the user himself. What about the network? What about the neighborhood? That is also going to be used to represent the neighbor, to represent a node when we are going to do the recommendation system. So now this is how the suppose a small graph is visualized using adjacency matrix. I hope you are aware of this, right? 4 nodes. How are their edge going to be defined? If this is 1 2, no, I'm going to use a laser pointer, sorry. 1 2 3 4, 1 2 3 4. If there is an edge between 1 and 2, this will be 1. If there is no edge, this will be 0. A simple adjacency matrix. How do we define a basic graph? So the idea again was very similar. This is the graph network. My objective is take all the features of the users, all the features, whichever I discussed, the 5 features for Kamala and Abhishek, all the 5 features are being used to represent an embedding in space. Embedding is nothing but a vector. If you have taken 2 features in XYZ, in XY axis, you can represent. If you are taking 3 features, XYZ axis, you can represent. But the idea is more features you get, the more quality representation you can get, right? So I'm going to not only focus myself to 2 or 3 features, it can be hundreds and 300s and thousands of features. There are very hidden patterns also, hidden similarities between folks, which we might not visualize, but there are something very similar to them. The models are very smart enough to figure out the dependencies. So I can have very huge number of features also, right? So that can be if the n is equal to 100, this can be a 100-dimensional space. And if u and v are very close to each other in the graph network, the vector space also, they will be very close to each other. It's not that you will be here and we will be here. No, since they're connected, their representation will also be very similar, very close in the embedding space. Fine. So now we have developed the foundation to graphs. What is graph? What is the graph networks? How the nodes and edges are created? How do we basically find out the embeddings of the nodes profiles? Now we are going to see what is the computation graph. So why do we need actually the computation graph? So adjacency matrix nearby values we considered. Yes, obviously. So adjacency matrix give you the information about the neighbors, the immediate neighbors, right? And hidden patterns means we identify insights or preferences, right? Of course, there are lots of preferences which are hidden, which we cannot define, right? Maybe Camilla likes something, okay, some specific Hollywood or Bollywood actor or actresses, and maybe Abhishek also likes the same. So that feature again can be a common. We cannot define that, okay? That okay, there will be a separate column that this is a user whether you like or not. There can be lots of features, right? So those hidden features, hidden patterns, there can be a lot of hidden patterns also. Those things are basically nothing but features. Those things are going to be used to represent them in the vector space. Having said that, right, so now we discussed how do we represent the word in terms of vector, how do we use all the information about the user to represent the user in the embedding space. Now we are not only going to focus on user's profile but also on the user's friend's profile, right? Assuming I is suppose Abhishek. So this is, I'm going to find out the computation graph of Abhishek. What do we mean by computation graph? Computation graph means nothing but the neighborhood of Abhishek. That is going to be the computation graph of Abhishek, because as I told, there's a very common proverb in English. A man is known by the company he keeps. So I know about Abhishek. Now I also want to know about Abhishek's friend. Only then I'll be able to know Abhishek more nicely, right? Because maybe Abhishek has something in his profile. There are something which Abhishek has not revealed. But if Abhishek is connected to his friends and his friends have some similar common interest, that can be also used to represent Abhishek uniquely, right? So we not only focus on the user's profile, we will also focus on the neighborhood profile to find out the Abhishek's vector representation, right? That is what computation graph is all about. So you can see, if I want to find out the computation graph of this node I, this will be nothing but the neighbors of I. That is this node, and this node, this node, this node, and this node. If I want to find the computation graph of this node, it will be nothing but the neighbors of this node, this and this node. Likewise, so all the neighbors features are going to be taken, which is nothing but vector. Aggregate them. Either you perform the summations or means. Lots of advanced aggregation methods are there, and you find out a single vector. That vector will represent Abhishek as a whole. Very basic example. Abhishek here is connected to these three folks. Suppose from Alma Better, these folks from Alma Better is connected to some other friends, right? So Abhishek, I know about Abhishek. Now, since I know about Abhishek's friend also, because they will also have a separate profile, I will take their vector, okay, and aggregate them with Abhishek's profile. So what happens? I'm going to get the information about their interest also, right? I'm not only going to get information about Abhishek, but also their friends. That means I'll be able to understand Abhishek much more better, right? Mutual friends, like friends of friends. Yes, exactly. That is what happens, right? Friends of friends. So this is the mutual friend, right? I am his friend, and he is again, he is his friend. So this, he can be suggested as a mutual friend. He can be suggested in mutual friend, right? That's neighborhood. So which means, again, before I begin, you are going to be identified not only by your profile, but also by your neighbor's profile, the friends in your friend list. Fine. Now, how is the computation going to take place? This is suppose a network. This is the target node A for Abhishek. Okay, so yeah. So Abhishek has B, C, and D in his friend list. B, C, and D in friend list. This C again has E and F in the friend list. E right now is not in the friend list of A. How do I find out the representation of Abhishek? So each one of the nodes, either it is A, B, C, F, E, or D, has created an account on Facebook. They have their own user profile. The informations on the profile, as I mentioned, name, address, interest, occupation, schooling, all those informations are available in the profile. Use those informations to generate feature embedding for each user. So for, I'll go to A's profile, I'll create the embedding of A, which has only information about A. When I say embedding, I mean the vector, the values, right? Suppose I am taking feature to be 50 features. So 50 values you will be using to represent Abhishek. I'll use again the 50 values, which is the vector, to represent B. How do I get that? Using the information of B. Using the information of C, D, E, F separately, all of them have their own personal profile. And that profile is converted to a vector embedding. Now, for my recommendation algorithm, I have to focus not only on that person, but also in his neighborhood. That's why we need the computation graph. So when you see A, if I want to find out the embedding for A for my recommendation system, what I will do, I will see what are the neighborhoods of A. So the neighborhoods of A are B, C, and D. So I can see B, C, and D being covered here, right? Now, who is B connected to further? So B is connected to A, C. So A and C are again feeding into B, right? Who is C connected to? C is connected to B, A, E, and F. They are also having here. Similarly, who is D connected to? A. It comes here. I am focusing on only two hops. Okay. These are the number of hops we have to define. I am focusing on only two hops, which means my friend and his friend. I'm not going to focus on my friends, friends, and friends. There's a very interesting fact. So Facebook also is not going to focus on your friends, 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 and friends, because in that case, it has been said that if your hops is equal to 7, means after 7 hops, if you're focusing on 7 hops, I'm going to focus on my friend, his friend, his friend, his friend, his friend. 7 times if you go, then you will be covering the entire network itself. Then there will be no difference between me and you. We will have they will our embedding will almost be very similar. So there is no point of having a recommender system. So the number of hops to be defined, how many friends you are going to consider your friends and friends. That's it. N equal to 2, n equal to 3. That is the thing. The n equal to 2 is basically optimal, or maybe 3, but n equal to 7 or higher n when you are going to take the number of hops, then the embeddings will be very similar to each other, because everybody will know about every other nodes in the network. And that means the embeddings will be very similar, and that does not make sense, right? So we are going to focus on only friend and his friend, two levels. So the features of A and C, when I say feature, I mean the vector. The vector of A and C are going to be aggregated to give one vector. Okay, this black box is nothing but an aggregation function. It can be a mean, it can be average, or it can be anything. Lots of complex aggregation can also be there. I am hiding that to remove much technicalities, right? So I'll be discussing what is behind the black box. They will basically take the two vectors of A and C, combine them to generate a new vector, which will capture the information about both A and C. I told you, right? The context is being captured when you are doing the vector addition. This is the beauty of embeddings. So when I have an embedding for A, that represents the properties of A. I have an embedding of C that represents the property of C. I aggregate them, I get an embedding which will represent the combined properties of A and C. That will basically be fed to B, which means now B is aware of A and C both. B has its own embedding, aggregate that also, which means I get to know about B, A, and C. That is being fed to A. Okay, so now A plus the embedding of this is going to be aggregated. Similarly goes for other also. If you focus on C, the embedding of this will be aggregated here, combined with C. That vector will also be aggregated with A separately. So you get that the neighbors aggregation vectors are also getting aggregated to define U. Likewise, so that is what it's telling, that neural, these blocks are nothing but neural networks. So neural networks will help you to perform some aggregations of the embeddings. And this is going to be the computation graph for every node in the network. So all of these nodes will have their own computation graph. So in the first slide, this was the computation graph of A, because A was in the root. Now you have computation graph of all the other nodes. You can see there are 6 nodes. So there are 6 different computation graphs. Idea is very simple. You focus on who is your friend and who is their friend. That is how you are going to create this graph. You start from the bottom, you take their embeddings. How do I take their embedding? I have their information, convert them into embedding and feed them forward. Okay, this is called message passing. You're passing the messages from low level to higher level. And in the neural network, you're doing aggregation. Two concepts: message is being passed, aggregation is being done. That is how we are going to represent the nodes very uniquely, right? So what is in the black box? So black box is doing nothing but average message from neighbors. Small mathematical thing I'm going to discuss, right? There's nothing so rocket science involved here. So not much complications, very simple. The idea is you're going to aggregate. So this is the aggregator, right? For a node V, suppose for a node A, I'm going to aggregate all the neighbors, embeddings of all the neighbors of U. So U is nothing but neighbors of V. Who are the neighbors of A? B, C, and D. So their embedding is going to be aggregated and mean. This is mean, right? Number of neighbors is 3 here. So all the embeddings divided by 3 plus there will be some constant vector dot the embedding of the node itself, the embedding of A itself, right? This is the aggregation function, and this you're going to do for all number of layers. How many layers are there? We have 2 layers. So at this level also you're going to do this function. At this level also you're going to apply this function, right? So first layer and second layer. So 2 layers you're going to do these aggregations. I'm not going to dive deeper into detail. Maybe this will be very exhausting, but if you see the slides, it's very simple. For multiple layers, we're performing these same aggregation functions. Your neighbors, take them, average, and add my feature also. Then I'll be knowing about myself better. Now, coming to the interesting part. I generated the computation graph of all the nodes. I know about my nodes and neighbors very nicely. I have my own representation. When I say now my final node embedding is capturing the information not only about me, but also about my network. So this becomes more easy to represent a node in the vector space, right? So now, since I have captured the information of myself and also my network, so the embedding is of very better quality. Now what are you going to do? Now for any random embeddings in your location, suppose for any user in your location, back again. Okay. So what I was saying is, once you have computed the once you have performed the aggregation, this was the computation being taken place in this box, this black box. This is the black box for you. I have unfolded the black box. I have opened the black box for you. This is what is going to happen there. Layer wise aggregation. So this is the first layer. You're going to aggregate them, add with B. Again, that vector you're going to forward here, message passing, aggregate them here, right? Now, this, after doing this, similarly for A, for all the nodes, A, B, C, D, E, F. Suppose I have 5 nodes in the network. All of these goes through these processes and will have their own representation that has captured the context, not only of the user, but also about the network. So what happens? Now, if I have any random profile in the Facebook, I'll find out the similarity between the node embeddings, right? Similarities. There are lots of features on the basis of which similarities can be defined, right? So I have used 50 features. The place of work, the schooling, the interest, the pages he follows, the groups he follows, what are the organization he's participated in, all those features, right, are being used to generate the embeddings along with the network. Now, this with any random, so this is suppose Abhishek's profile. So what happens is there will be a random profile, okay, to optimize it. Suppose in Abhishek's location. Right now, Abhishek is in, suppose his hometown is in Hyderabad. So a specific locality, whatever profiles are there, that profile based also on the mutual friends, right, is going to have a separate embedding. So we will calculate the dot product between the two vectors. Is there a similarity between these two? Is Abhishek's interest and Abhishek's features, whatever we have, matching with the person X's interest? There will be a threshold defined. If this similarity score is above a specific threshold that we define, right? There are also processes of defining the threshold. Then we say, okay, this is a high chance that he knows Abhishek. Better recommend him, right? There are questions. Why ML models are considered black box? Okay, so you want me to? So this is we are not considering ML models as black box. This is for the simplicity of this presentation, right? Not to make it complicated. When I'm saying black box, I cannot show the entire computation here. So I just made a box just to show that, okay, what is going behind the scenes. So what is a black box? A general term we use, to abstract something, to hide something, so that you can just focus on the simplifications and not on the complex computation which is going behind, right? So if you are using a Facebook, suppose a normal person is using a Facebook, he has no idea about the network, right? What is going on behind. So for him, I can say this is the black box. What is going behind this? There's a training going behind this, right? We are generating embeddings. So to make things very simple for him to understand, I have told that this is a black box. But what is going behind the black box is this aggregation. Is this the only aggregation that takes place? No. Technology is evolving, algorithms are evolving. There can be more enhanced weightage of this aggregation. Right now, I am simply aggregating A and C with B, right? There can be different types of aggregation also. What can I do is, my vector can say, okay, I will focus more on the feature of C and less on the feature of A. Okay, I'll focus more on the vector of B and less on the vector of C. I'll give weightage to these vectors. This is also possible. There are algorithms for that. But for keeping it to be more generalized and specific, very simple, this is a basic aggregation that we are doing. But Facebook might do more complication aggregation. This will not consider all the nodes similar, right? Right now, I'm saying for me, B is also a good friend, C is also a good friend, D is also a good friend. All those three are friends for me. I don't differentiate them. But maybe this can be a very special person for you. B, very special, right? He's someone who's a very VVIP person in your network. So you might get more weightage for him, okay, and they might get some less weightage. So again, their embeddings, if they are getting more weightage, will have more influence on your embedding, right? So I hope that answers the question. Yeah, we are abstracting it. Black box is nothing, but we're just making it simple. Okay, this is the complexities behind the calculation. Now, since we have performed the similarity scores between the vectors, now you find out, right? If my dot product is satisfactory beyond the threshold, okay, there's a high chances that this person is in my network. So I'll suggest him in the recommendation. That's why every morning when you wake up, there can be hundreds of whatever dot products I'll calculate with the embeddings, which are, suppose there are nodes which are not in my friend network. I will calculate their embeddings also, my embedding also. Their final embedding, my embedding, right? Now, every night maybe, right, there are algorithms which takes place at which runs at night, right, because at a time the traffic is less. So maybe that time what happens is they will be finding the dot products of the vectors, right, and you'll find out whether there is a very similarity between them. If there's a similarity, you store them, sort them on the basis of similarity. The vectors which are had very good dot product, which are very more similar, should be recommended first. So you will find out recommendation of top 10 people today. Again, tomorrow you'll find out another top 10 people. This is how the ranking takes place, and the suggestion keeps on moving. And there's a high chances that you might know that person, right? Because now we have captured the context, right? Based on your location, based on your features, your interest, your hobbies, the people you follow, your network, everything. So we are taking the dot products of the vectors now, finally. And this is a very basic method I'm saying, the aggregation, right? There are a lot complex method, but the fundamentals remain the same. This is how you represent the graph. This is how vector representation takes place. This is how you generate node embeddings and you do the dot products. Finally, when you find out the dot product of two vectors in that n-dimensional vector space, if they are very close to each other, they will be recommended in your Facebook friend suggestion. Is that clear? No, threshold is a specific value we have to define, right? So they define, suppose if the similarity is more than 70%, 0.60, okay, then we can say, okay, if it is similarity product, dot product is, but you have to squeeze them between 0 to 1, normalize the value. Okay, dot product can have any values, but you have to make sure you normalize them, put them standardize the value to between 0 to 1, so that you can predict if the value after standardizing it is between 0 to 1 is 0.6, high chance he can be my friend, or zero point 0.7. If it is 0.7 or more, then you can basically add him, recommend me that particular guy, right? That's how the thresholds are actually defined. So this was about the Facebook friend recommendation system, the very basic about how graph networks and your network information can be used to get the Facebook friend suggestion. To summarize the Facebook friend suggestion, every user has a feature for them. Each of these features is nothing but a vector we can represent. We will aggregate those features to get one vector for this user, right? Because this user has age, gender, language, hobbies, and lots of stuff. Take those words, convert them into vectors, you get a vector representation of this node. Now these vectors, these nodes are connected in the network. Apart from their information, also take the information of the network. Remember the computation graph, take their embedding, you will generate the embeddings for all the nodes. Find the age likelihood. What is the likelihood that there will be an edge between them? If it is satisfactory, beyond a threshold, we will suggest them, okay, there's a high chance there's a edge between them. We are ranking them, okay, based on the scores of similarity, and the top 10 basically is going to be recommended in your Facebook. The next morning you open Facebook, right? That's how basically a very basic idea about how graph networks can be used for recommending friends on Facebook. So this was the very first part of the session where we were discussing about friend recommendation engine. So I would like to know from the audience now, how much is it helpful for you? How much was it intuitive? Yeah, social media, obviously this was for Facebook. It can be helpful for LinkedIn. It can be helpful for your Instagram, Threads. I am not on Threads. Twitters, people you may follow, right? So these are the different platforms which uses recommendation systems for recommendation systems, right? So this was the first part of the session where we have discussed about friend recommendation using graph neural network. I hope this part is intuitive, right? And I hope you still have energies left to go on with the next part of recommendation, which was Netflix. Yes, very good for basic understanding. Thank you very much, because that was my objective, to give you interest on how the graph networks embedding. So you remember, right now we have covered the informations like word embedding was very basic, right? I could have skipped that, but I did not want to skip it, because that is the basic of node embeddings, right? You should know how word is basically converted to vectors using the context, those aggregated to represent the node. Not only the node's information, but also the network's information is being used to generate the embedding, and finally the similarity between them, and you get the recommendation of friends in a very simple level. Since technology is evolving, mathematics are being advanced, the algorithms are improving, so the structure is going to be same, the process remains the same. Only changes which you can expect is in terms of the computation. They will definitely follow graph neural network, right? No way graph, there's no possibility to solve these problems without a graph. What I feel, because you have a huge number of users of Facebook, the very best way to deal with them is using graph network, right? So graph network makes things very easy for you, because you can visualize them, you can run lots of queries, and it makes things very simple. So only enhancement possible is in the algorithm that you're using to compute the embedding. That is the research where it goes on. How can I represent a user more and more better way, in a more and more better way? That is where new algorithms come up with new tweaks, right? The computation graph that we were talking about, the black box the function behind the black box can be changed, right? We can have different aggregation functions. There are lots of graph convolution network, graph sage, lots of algorithms. So it's very interesting. If you are want to go in the direction of graph network analysis, I would follow you. I would recommend you to basically dive deeper into the different models of graph neural networks, right? So uh, some comments. Yes, basics were required about how the graph network information is used in embeddings and how embedding is actually done. Okay, next part, eagerly waiting. I'm also excited. I hope you have any further delay. Content recommendation, right? So right now we discussed about Facebook recommendation. That was altogether a different platform. Facebook friend recommendation. Facebook also recommends contents, right? Facebook also recommends content. Maybe you might get some posts on your net on your Facebook. Maybe on Instagram also you get some posts on your newsfeed. Similarly for Netflix, when you open, there's a big, you know, big thumbnail there. A movie is going on, and you have some different rank wise sorted movies, right? So all these things are part of content recommendation, and it is not only limited to Facebook, Instagram, or Netflix. We also have e-shopping platforms, Amazon and Flipkart. As I mentioned in the beginning, if a customer is coming to your platform and you're not able to satisfy him in the first 10 seconds, he's going to leave. He's not going to come back again. I will definitely not come back. If I open Netflix and I don't get the movies of my interest, I'm definitely going to come back. So any resources like websites or books for understanding social media analysis, definitely I'll share in the end of the section. In the end of the session, please let me know. I'll let you know about the things. Okay, I'll share the references. So content recommendation, why is it actually the need of the hour? Why does Netflix use the recommendation system? This particular paragraph, this statement is coming from Netflix itself, right? So Netflix says that they have about 90 seconds. Let me use a laser pointer. So Netflix says that they have about 90 seconds to grab a customer's attention. I'll open Netflix. You have 90 seconds. Each second plays a key role. In 90 seconds, if I'm not able to convince the user for a movie, he's going to come out of Netflix. He's not going to bother watching Netflix again because I don't get movies of my choice. What if I open Netflix and I get only Korean movies, right? Or what if I get only German movies? I don't understand Korean, I don't understand German, and all the movies that I see are from the same languages. Apart from that, what if I open Netflix and I see all the shows made for kids, not of my interest? Now I am no longer a kid. I don't get much interest in watching kids shows, right? Or animated shows. So again, it is a time waste for me, right? So the idea is based on the user, based on his preferences, based on his interest, you should recommend me movies. I'm interested in sci-fi movies. I like thriller movies. So all those sort of movies. When I open Netflix, I should get those movies in recommendation. So this Netflix, you can see, this is obviously not from my account. Okay, this is a random image from Google. So you can see when this guy has opened his Netflix, they get some recommendation, right? So this recommendation comes only based on his interest, right? Because he has watched similar movies, and that's why he's getting. So the Netflix, the company says that when we have only 90 seconds to grab a customer's attention, okay, and 80% of the success rate, the 80% movies which are watched on Netflix are because of the recommendation system only. It's not that the user actually wanted to see that movie. It's just because Netflix recommendation engine suggested that movies. The user went and clicked that movie and he started watching that. So 80% of the business of Netflix, 80% success rate keeps the subscribers happy. Netflix says that it can lose 1 billion or more every year from subscribers quitting its service if they don't use a recommendation engine. So recommendation engine is the bread and the butter for Netflix, right? If you don't have an efficient recommendation algorithm, I'm sorry, you're going to lose business, and you can see $1 billion loss. That's huge, right? So yes, exactly. Now let's discuss about the different types of recommendation algorithms that is being used. We have collaborative filtering, we have content based filtering, right? When we focus on collaborative filtering, what does it mean? It means that suppose this is Abhishek and this is, I just forgot the name, sorry, Camilla, right? Suppose this is suppose this is Raj, this is Simran. Now Raj basically watches some movies, Simran also watches similar kind of movies. They might don't not know each other, right? Raj suppose stays in Mumbai, Simran stays in Delhi. They don't know each other, but there is a very common similarity between them. Raj has watched these movies. Simran also has watched these movies. Similar taste. This gives an idea of similar taste. Now, if today Simran watches this movie, what happens is recommendation engine tomorrow. What it will do is will recommend Raj also this movie. How does it do? It does that because recommendation engine is smart enough to understand that since Raj and Simran so far had a very similar taste, they used to watch similar kind of movies. There's a high chance that if Simran had watched this movie today, Raj will also like that movie. This is called collaborative filtering, which is based on the user's view, right? Content based filtering focus on Raj itself. Raj watched, suppose, Interstellar today. If Raj watches Interstellar today, tomorrow maybe he can get a recommendation on Gravity. Why? Because there is a very similarity between the movie Interstellar and Gravity. Sci-fi movies, science, space, all those stuff, right? Those are the features of this movie. So now these things become very simple for you to understand. Assume in terms of embedding. User. Raj is a user. This is the Interstellar movie. Interstellar movie has some features. What are the features? What is the genre of the movie? It is a sci-fi movie. Secondly, who is acting there? What is the movie all about? Space exploration, right? Time exploration. Come to Gravity. It has also its separate features. Space, sci-fi, science involved, lots of science fiction involved. These are the features of the movie Gravity. Don't you think if I use the features of Interstellar and represent in a vector space, and I use the features of Gravity and represent them in a vector space, they will somehow be very close, right? They will definitely be somehow be very close because we know they are very close to each other, right? Because their characteristics, their features are very similar. So you can visualize in terms of embedding that the embedding of these two movies are very similar and their similarity score is very high, which means there is a high chance this is liked by him. So this will also be liked by him because he likes movie of this kind. So all those movies which are closer to this movie in his network, in the neighborhood, will be suggested to Raj. So far, so good. You can relate the problem to the embeddings here also, right? The vectors, the features of the movie is being used to represent a vector, and we can see how. So what happens is, suppose there is a vector space of movies itself, right? So we have a vector space of movie itself, and we have a particular user called, we have a particular movie called Interstellar. Interstellar had lots of features, the genre, sci-fi, who is acting there, what is it all about, all descriptions. Using those features, we aggregated them, got a vecting, we got an embedding. So Interstellar in the vector space is at one particular point in vector space. Use the features of Gravity also, aggregate them, perform vector operation, which I told you, convert them into vectors, aggregate them, get a vector embedding. This will also be a part in the vector space. What you will find out is Interstellar, Gravity, and take any other sci-fi movie names. They will be very close together in one particular community. There will be a cluster of those nodes. So what happens when the user watches Interstellar? I'm going to go in that node graph network. I'm going to find out what are the neighborhood of Interstellar. What are the nodes very close to the Interstellar? Those nodes can be used to recommend Raj because those also are similar to Interstellar, similar taste. That's how content-based filtering actually works, and that's how collaborative filtering actually works based on the similarity of the users. Okay. Yes, similar to space the category, that is also one of the feature. Now, content-based recommendation, which is what we are going to discuss. So, content-based recommendation. So, content-based recommendation was this, right? So, Raj liked this movie. Raj liked this movie. So, the other movies which are very similar to this will be recommended to Raj. That since you have liked this movie, you will like this. So that's why you can see Netflix. There are options that top picks for Luke or top picks for nowadays. What they say is the movies you may like, right? Something like this comes up when you open Netflix. You can open it and see now there is an option, movie you may like or something of your interest based on your interest. These are the movies that has been suggested. How does it? How does it that does that? Suppose here only. So this is the movies. Each one of them is represented by an embedding in the cloud in the vector space. Now, since I have watched this movie, okay, I have watched this movie. If I represent this in the vector space, I'll find these movies are very close to these movies in the embedding space because the features are very similar. And we know if the features are similar, the values will be similar and they will be very close in the vector space. That's why I'm getting a recommendation of these movies, right? Now, but now we'll talk about the we discussed about, right? We discussed about content filtering and collaborating filtering in this side itself. So that much is evident. This is clear how what is the difference between a content based filtering and a collaborative filtering. So any users watched movies based on either user's interest base or similar user interest like individual choice versus impact of the other users. Perfect. That's it. So either you will watch movies based on your interest is being tracked, okay, but it's not possible that you will like all the movies. You have watched all the movies, right? So some movies you have explored, some movies other guys have explored. You guys have similar taste. That's why I'm recommending it easily. Okay. Let's now quickly jump into a very interesting problem that had popped up in 2006. Okay. In 2006, this is a very famous problem, Netflix price competition. So Netflix in 2006 had come up with a problem statement where it told that we are currently using an algorithm called Cinematch. So Cinematch were using some statistical analysis, okay, some linear vector combinations, vector representations. Also, there was also so Cinematch was using some fundamental algorithms which had some shortcomings. Also, it was not that advanced. So they wanted to increase their network. We know, right, how Netflix has evolved gradually. There's a blog on Netflix history, how Netflix has gradually evolved with a 230 million subscribers right now. How has it evolved, right? So the starting was not that easy. They had a very basic model for recommendations. Say, for example, maybe I can say the first time they were subscribing to Netflix, Netflix will ask set of questions. What is your interest? Which type of movies you like? Which languages you know? Who is your favorite actor? All those things were taken as input, suppose. And sorry, all those things are taken as input. And then Netflix used to recommend the users based on the inputs it has taken from the users by putting some conditions, filtering them. This is not that convenient approach. This is not an optimized approach, right? Because I would never go and fill the entire Google form. I don't even fill a Google form. When it comes up, you fill the forms, you show them the interest, you have to tell your interest manually. No, the algorithm should be smart enough to find out my interest itself, right? I will not define, okay, that I like this movie, this movie. No, whatever movies I like, whatever movies the users of my taste like, based on that, you should recommend me movie. I'm not going to enter, I like this movie, I like this actor, I like this actress, I like this kind of movies, this genre, sci-fi, nothing. The pattern has to be captured. The pattern of watching the movies have to be captured. The pattern of guys who have similar taste of movies like me has to be captured. Based on that, you should recommend. So the price for this particular problem statement was $1 million. Netflix was ready to pay $1 million. Netflix that time was a startup, right? And they were ready to pay a price of $1 million. Yes, they have advanced, right? So why should a user pay for DVD even if he does not watch by taking DVD later? They decide to go online by following watch on demand principle. Fine, on demand service. So before they had DVD, right now they have, they don't have to buy DVD. Everything is on cloud. Whatever movie you like, lots of movies to watch. You can watch. $1 million was the price to solve this particular Netflix recommendation problem, and they gave a time of 5 years. So I'm giving 5 years time. I'm giving a prize money for $1 million to anyone who can beat the current algorithm of Netflix by 10%. So you have to improve the performance of Netflix by 10%. Mind you, even a single percent improvement means a lot in terms of recommendation, right? So they were talking about a 10% improvement in the accuracy, or you can say 10% reduction in the error of the prediction. Okay. So the data set that they gave was having users and user ID, and there were about 17,770 movies and 480,000 users data they had given. They had not revealed the information about the users, just a user ID, the movie ID he has watched, and the date, right? The date on which he has watched, like that. So, so Netflix price was solved by this team. The Belcos Pragmatic Chaos was the name of the team. These 7 folks here on the screen had basically won the Netflix recommendation prize. Very smart enough. The beauty is behind the algorithm that they used to solve this particular problem, right? So the $1 million problem of Netflix was solved. Mind you, the current algorithms of Netflix are much advanced, right? It has evolved, but the basics always remain the same. This was their bread and butter. The traditional algorithm which was developed by the team is being used, but with lots of enhancement. They're trying to evolve it, use deep learning concept, use reinforcement learning concept. Okay, the interaction between the users and the movies and the Netflix account, all those things are captured now and being combined with the traditional algorithm that they have decided. We are going to discuss about the traditional techniques of Netflix Netflix recommendation engine. What is the foundation? What is the basic idea behind the recommendation tool? So these guys took home $1 million. What was the input data given by Netflix? Netflix had given the inputs of user ID, movie ID, and the rating given by the user to that movie. So you have a huge list. Okay, I told you lots of users, 480,000 users, close to 18,000 movies. So you get a user ID, you get a movie ID, you get a rating for the movie. All these data were available, right? And now the idea was to reduce the error. How do I reduce the error? Suppose I give a particular movie I have not watched a rating of, so I want to know, okay, so I have watched the movie, I have given it a rating of 4. Okay, now I am saying you I have not watched that movie. I'm telling you a lie. I am telling you that I have not watched that movie. So how much do you think I will rate the movie? Okay, so you will ask me what are the different types of movies you have watched. Okay, what kind of movies you like. Based on that information, whichever he asks me, he will say, if based on your history, I can say that if you watch this movie, you will rate him 2. Now I know that I rated it 4, but the computer suppose is telling me based on my profile that I'll rate it 2. There's a difference. Actual value is 4, model is predicting 2. What does it mean? There's an error. So the difference between the actual value and the predicted value is the error. So what is a metric to be defined to say, okay, the recommendation engine is actually performing well, right? How will you understand whether the current recommendation engine is actually performing well? So traditionally, what they did was they were using root mean square error. Very basic. We are going to use a metric, root mean square error, which means the actual value. Okay, that because the data set, since Netflix is providing the data set, they are aware about the rating given by the user. What they will do is they will remove some rating. They know what is the rating, but they will tell the participants of the competition, they will tell that I don't know the rating of this, but somewhere I know what is the rating. I just want them to predict what will be the rating, right? And finally, how do I test whether their model is performing good? I'll take the actual value, I'll take their prediction, and I'll find the root mean square. So this is the mean you're taking, mean square. So the number of movies I have rated, their predicted value, their actual value minus predicted value whole square by number of movies I have rated, its root of that. This was the root mean square error. The objective is to reduce this error as much as possible. As per the competition, the idea was to reduce it by 10%. So you have to reduce this entire loss by at least 10%. So your performance should be enhanced by 10%, or you can say the loss must be reduced by 10%. I can't use customer satisfaction as a metric for recommendation. Like, how would I know if my recommendation engine is working good? Okay, I'll ask the customer. Sometimes customer don't even rate. After the movie, they will not even rate. I don't rate because we are so lazy to rate, right? Sometimes, okay, how much will I rate the movie? I'll skip that part. So customer satisfaction was a hard to gather data, right? Prediction effectiveness, that's it. So recommendation, how well is my recommendation engine performing? You cannot be dependent on the user for that feedback. Okay, so they had basically used a metric called root mean square error. They told, I know what the rating actually is. Okay, I want the participants to come up with a value, their prediction about the movie, and tell me whether, and I will check whether their prediction and my actual value is correct or not. If it is very close, less number of errors, you're going to take the money home. So this is the problem statement. Let me see the chat section, some inputs. Cost function should be minimum in order to drive users view or watch. Perfect. So it seems you have good understanding about the loss function, the cost function or loss function. Correct. So this is the problem statement. You have a user. Suppose I have 6 users and I have 8 movies in Netflix. Let's make the data set very small. Not everyone can watch all the movies. User 1 has watched 5, 2, and 4. So user 1 has watched movie 2, movie 4, and movie 5. User 3 has watched movie 2, movie 3, and movie 5. These are the ratings that they have given to the movie. Based on this data, what the Netflix did was they had the entire data. They had suppose this entire details, this data. Suppose Netflix had this value also, but they desperately what they did was they deliberately removed this value because they want the participants to come up with a model to predict what will be the value of this. When I say what will be the value of this, which means I want to ask them, user 5 user who has ID 5, when he watches the movie 3, what do you think? How much review is he going to give? How much review is he going to give? That is the question. That is what you have to predict. I know because I am the Netflix owner. I have the problem data set with me. I know that the value is 3, but I want them to predict the value to be 3. Even if they predict 2.5, it is fine for me. As close as possible. What if I know it is 3 and they predict 5? That's wrong, right? That's too much difference. So they need to come up with algorithms so that they can predict these values. And if they predict this properly, I can understand the patterns of the users, right? Yes, missing values has to be computed, right? So missing values has to be computed. That's where the computation comes. This is the mathematics involved. I will not discuss it right now. I'll discuss it towards the end. Okay. I want to make things simple for you with this. Okay. So I don't know why this is not hiding. Sorry, I'll not be able to see questions now. Just a minute. I hope it's visible now, right? Fine. Please give a quick confirmation if it's visible.
Yeah, it's visible.
Thank you. Thank you. Thank you so much. So, yeah. So now let's just create the problem statement. Okay. Now we are going to create the problem statement of Netflix recommendation system. So who are the entities in the Netflix? So we have movies, we have users. That's it. So users and movies, these are the participants in the Netflix environment, Netflix ecosystem, right? So let's make the data set very small. We have millions of users right now, more than 200 million users in Netflix, but right now we will stick to very 5 users. Suppose there are 5 users of Netflix, and right now Netflix has only suppose 5 movies. Okay, so these are the users of Netflix who has subscription of Netflix, and these are the 5 movies. Now, what we want to create is a matrix. Okay, so this user, after she watches movie M1, what is the rating she can give? Or suppose she gave a rating of 3. She watched the movies in suppose yellow, and this movie suppose she has not watched. So suppose she watched movie M1, so she gave a rating of 3. She watched M4, she gave a rating of 3. She watched movie M5, she gave a rating of 1. And this suppose she has not watched, but you want to recommend this rating, right? So this is the user, this is the movie, this is the rating given by the user to that specific movie. Okay. Uh, are there any future checks on the movie to be recommended, or it solely depends on the user watched movies? Yes, yes. So it does not only depend on your personal test, but also on the person's history, watch history, who has a similar taste of you. That's what we are going to discuss. So you see Simran here has the she has given this following reviews to the movie M1 to M5. She has given a review of 3, 1, 1, 3, and 1 to movies M1 to M5. Raj also gives quite a similar recommendation to review to that movie, which means Raj and Simran has a similar taste. They have a similar taste. So the user embedding, if you take out, okay, they will be very similar. If you vectorize it, they will be very similar, right? Because their review that they have given to the movies are very similar. Moreover, there can be similarity between movies also, right? So if you see M1, the users, these 4 users have given the rating 3, 1, 3, 4 to M1. And these same users have given a similar rating to movie M4 also, which means if this you are considering as a vector, and this also you are considering as a vector, vector M1 and M4 will be very close to each other, which means there is very similarity between the movies. For example, if M1 is equal to mall cop, F4 is equal to observe and report, just looking at the thumbnail, you can find out this is something related to cop, okay, something related to policing and all those stuff. So since we can see the features are very similar, so they have a similar review given by us. So they have received a similar review which means there is very similarity in the movie, and hence you can see Molkov and the this observant report something is related to policing, and they have a similar reviews given by the users. Now, suppose this particular person loves action movies, the other person loves comedy movie, and this person has the review, which is a summation of the review given by first and second user, average summation. So 3 plus 1 is 4, 1 plus 2 is 3, 4 plus 1 is 5, 3 plus 1 is 4, 3 plus 1 is 4. So this user's review is based on the average of the reviews given by Raj and Simran. Suppose this is, I don't know if he's a male or female, but suppose he is Alex. Okay. So Alex's reviews pattern is the average of the review pattern of Raj and Simran. Okay. So whatever is the taste of Raj and Simran, the average of that, you can say is a taste of him. So since Simran loves action movies, Raj loves comedy movies, you can see the average of these two is equal to this, which means that this particular person here loves both action and comedy movies. Now, look at this bottom left. Movie M2 has received this review. Movie M5 has received this review. M3 has received this review. M5, you see, is the average of the review of M2 and M3. So M5 is a movie which has got a review which is the average of the review of M2 and M3. So M2 is suppose about a tornado event, something related to tornado. This is something related to shark. Okay, very thriller movies. So the average of this is equal to suppose Sharknado. This is a movie which has average of the content of this movie and this movie. Interesting. How do we look this in terms of embeddings? Twister movie has its own embeddings, own features. What it movie is all about: tornado, disasters, okay, thrillers, suspense. All those things are nothing but features of the movie. What this Jaws is all about: sharks. It has thrillers, it has climaxes, all the stuff. They will be represented in a vector space. Average of this, because since this is a combination of these two, this will somewhere lie between these two, right? The embedding of this movie will somewhere be between these two, right? This is how you see this in terms of embeddings. Now, the question is, we know the pattern of Simran, right? We know the pattern of Raj also. We know the movies watched by other guys also. Now, since I'm familiar with the pattern of Simran, if Simran has given a review of moving 1 to M5, there's a high chance that Raj will also give the movie review 1 only, right? And if it is so, which means Raj is not liking the movie, and if he's not liking the movie, should I recommend him that movie? No, I should not recommend him that movie, because I know Raj will recommend it 1. So I should not recommend that movie, because this is something Raj would not like. He will be annoyed with that. Why did Netflix recommend me this movie? Because I don't like this. So the idea is Netflix will always recommend only those movies whose expected rating has been calculated to be good. If it has calculated the rating is very nice, they will recommend that to the user. How did they recommend? They know the patterns of in which the users are watching the movie. They know that Raj and Simran have similar pattern of watching the movies, and hence they are able to relate it. Okay, so again, now we are going to see them in terms of features. What are the different features of the movie? The different features can be a movie which has discussed about a sad dog, a movie which is a drama, a movie which has action, or maybe the movie which is discussing about a big board. All those stuffs are already present in the description of the movie, right? The trailer part, you can see they capture those movies, those information. Who is the actor, who is the actress, okay, whether it is a horror movie, all those are nothing but features. So now, assuming to simplify these features, so remember, embeddings require features, context, right? So a movie can have lots of features, right? Now for simplicity, I'm taking only 2 features. So suppose M1, M2, M3, M4, and M5 are my movies, and I want to define them on the basis of 2 features: comedy or action. Now, M1, how much I will rate in terms of comedy? So out of 5, I'll say 3. There are 3%, like suppose out of 5, 3 out of 5 it is a comedy movie, and 1 I'll rate for action. That means it has less number of action. Similarly, I'll generate features for all the movies. So these are nothing but features. That means it contains less of comedy, more of action. It contains very minimal comedy, but it is mostly focusing on action, because the value for action is 4. The weight to action is given as 4. These are nothing but features of the movies which we are generating, right? I'm generating only two features in terms of comedy and action. Now, I'll generate the features for the users also. What is the user actually liking? The user likes comedy movie or action movie. This user does not like comedy, this likes mostly action. So this can be treated as a value of 1 and 0. If you like comedy movie, give the value 1. If you don't like, give it value 0. Right? So 1 0 0 1 1 0 1 1. This means this user likes both comedy and action movies. What did we do right now? We created the features of the movie and the users, right? Based on some features, common features. The Netflix price competition was solved by the team using the matrix factorization technique. This is the mathematics involved behind the recommendation engine in Netflix, right? The traditional recommendation engine in Netflix you had used or uses the matrix factorization technique. The idea is, since I know about my user's taste from this, right? I know my this user likes comedy, this is not action. So 1 0 0 1 1 0 1 1. This is the matrix here. I also know the movie matrix, right? What is the feature of the movie? What is the movie all about? So how much comedy is there? How much action is there? These values. If I multiply this, the matrix multiplication, simply matrix multiplication. So what is matrix factorization? What is factorization actually? If I say 2 into 5 is equal to 10, the idea is how can I get 10 using these two values? Either I can have x into y is equal to 10. So x can be 2, y can be 5, x can be 1, y can be 10, x can be 5, y can be 2. These are nothing but factors. This is what factorization is all about. So now similarly, the idea is, so if you know about the user's taste, you know about the features of the movie, you can generate this matrix, and this will tell you what is the review you can expect the user can give this to this particular movie. This is the complete matrix. Now, what is the challenges with this? The challenges is the size of the matrix can be very much. So there are not only 5 users, 4 users. As I told, there are 230 million users right now in Netflix, more than that. And there are lots of movies, more than 10,000 movies on Netflix. So this again, if I look into the count of the users and the movies, so what happens? 1,000 movies suppose are there on Netflix, and each movie is defined by 100 features. Then the size of that movie matrix will be 1,000 into 100. The size of the user matrix, wherein the user's taste is defined, 2,000 users, and they are defined on the basis of 100 features. The user is defined on the basis of 100 features, 2,000 into 100. Now, when you do matrix multiplication, you will multiply this matrix with this matrix. So their size, if you multiply, it is equal to 2 million entries. 2 million entries. That's a huge storage space, right? In terms of matrix computation, right? That's how challenging is matrix computation. So you can visualize this in terms of graph also. They are the users, they are the movies. So if the user has age with all the movies, and every movie has all the users have age with all the movies, it's like a bipartite graph, right? So two groups, one is user group, one is movie group. Now you will give values to the ages. How much value will you give to the age? If I like the mall cop, I will give a rating of 4 or 5 accordingly. So these ages can have values, right? So in the adjacency matrix of user movies, you will be giving the values based on the value you have given to the age. You can simplify the graph by finding out the features, right, which you are focusing on. I am focusing on only two features, comedy and action. So does this user like comedy and action? Create a graph. Does this user like comedy action? Create a graph and give value. How much does it like comedy? How much does it like action? Give the value to the edges. Does this movie contains comedy and action? Create an edge. Yes, this movie contains comedy and action. So it contains 1% comedy, 4% action. One comedy, 4 action. These values can be set. Now, this is very interesting. This will make you understand the entire mathematics behind it very easily. Look into the very first matrix here. So the idea is, my objective is to generate this values, because I know this is the matrix which is going to let me know how much is this user going to like the movie M5. This value is going to let me know whether I should recommend this movie to that person or not. Do we have this matrix with us? No. What type of matrix do we have? We have sparse matrix. So we have matrix like this, right? So we have a matrix like this, in which some values are filled, some values are not filled. So our objective is to fill these unfilled values. Based on whatever values are filled, my objective is to fill the unfilled values, right? So what is going to happen is, right now I told you there are two features, comedy and action. There can be lots of hidden features also, right? So assuming I tell that there are 100 features of the movie, 100 features of the user, a user can have 100 features. So this will be four users, and there will be f1, f2, f3 till f100, f100 features, right? Do you know what are those features? I might know, I might not know also. There are some hidden patterns also, right? Some hidden patterns that actually influences my recommendation system. So I assume, so let me take very basic example. F1 can be what type of movie you like, action or comedy, that is a feature. F2, the actor or actress. F3, whether you're into sci-fi or whether you're into thriller, action movies, all those stuff. So all these are nothing but features. The location of the user is also a feature. Where does the user stay? That is also a feature. So assuming there are, for simplification, there are two features, F1 and F2. So this user is defined on the basis of two feature, and the movie is also defined on the basis of the same two feature. How much F1 is present in that movie? I mean, how much comedy is present? How much action is present? Right? This, we have this matrix with us somewhere behind the scene. I have this. Now, what I'm going to tell is, now for clarification, this matrix actually is not completely filled initially, right? It has some vacant spaces. Suppose this value is not there. I want to predict this value. I want to predict this value. I want to predict this value. So my model will take them, fill the matrix randomly in the beginning. Some random values will be filled in this and in this matrix. Random values that are basically the features. They will perform matrix computation and get the values of the matrix. This is the calculated value of the matrix. But I know my actual matrix looks like this. So if you compare the value, this is 3 here, but here, based on these features, which are manually generated, not manually, just randomly generated by the model, I got a value of 1.44. Is it correct? No. There is the error, right? So my computer first comes and it says that, boss, I have developed this model. This is how the review will look like. Then I know that I have not told the computer how the review actually looks like. That is my data set. I have hidden it, right? I know that this user had actually given the review 3, and you are saying me review 1.44. No, there is something wrong. So you have to adjust it. The model, this is a very basic understanding of backward propagation. The model will then go back, okay? It will say, how did I generate this value? 1.44. Now I am telling it that 1.44 is very less, right? Because I am expecting a value of 3. So you have to increase the value. So it will say, what are the features which has calculated the value of 1.44? This into this, right? So zero point 0.2 into 1.2 plus 0.5 into 2.4 is going to give you 1.44, which means I have to increase these values, right? I have to adjust these features. So you are going to basically increase the value. You can see you are increasing the values of these features only to increase the value of this 1.44. So model increases the value of those features, comes back again to you and says, boss, now I have predicted. Now tell me, is this value correct? Now again you say, no, I am still predicting. I know the value is 3, but now you are predicting, suppose 1.92. Okay, now you are predicting 1.92. Better than before, but now there's a challenge. What? Now this has gone wrong. This you are predicting 1.83, but actual prediction is 1. I know. This is too much, too more than 1, because I know the review is 1, but you're giving more than close to 2. So you have to basically adjust the parameters influencing this value also. What are the vectors which are influencing this into this? So they are going to decrease this value now and decrease this value also. Who? The model. So the model, this works in the terms of gradient descent. So as in the discussion, somebody had commented that they use the cost function. So what is the cost function here? The cost function, I told you, right? How will you understand whether your model is predicting correct or not? User feedback. But user feedback is not reliable. Nobody gives you the feedback, okay, whether I liked it or not. If I don't like it, I'll not come back to Netflix again. I'll not give them a review that I did not like your recommendation system. The best way is to calculate the using the training data. So in the training data, I have basically hidden the values. I know what are the reviews given by the users, but I will hide them for the model, and I'll tell the model to predict it. So the model is predicting this, right? You can see the model predicted this based on these features. And I saw that, no, this is wrong. Why? Because there are lots of errors. How much error is there? So this 3 minus 1.44 whole square. So mean square method plus 1 minus 1.37 whole square plus 1 minus 0.2.26 whole square. So likewise, the actual value minus predicted value whole square for all the values in the matrix you're going to do. This is what is going to be the value of your error. How much error is there? You can calculate that way. So the model every time goes back and adjusts the parameters. These are nothing but parameters. So if you look in terms of neural networks, the weights are getting adjusted. That's altogether a separate discussion. But what goes in layman terms is the parameters gets adjusted so that the model will finally one time after some thousands or 100 or 500 of iteration will generate the matrix which will be very close to the matrix which you are actually expecting. That is a training phase. I'm expecting 31131, so maybe the model will give you 2.7, 0.8, still very close. The loss is very less. And as I told you, Netflix had told, if your loss is improved by 10%, we are fine with it. That's how the loss function was calculated. You can see loss function is the actual value minus the predicted value of the model whole square. So loss function, you remember the maxima and the minima which we had studied in our higher schools, that how do we find the maxima and the minima? If I want to find the value for which the loss is minimum, I want to find the value of these parameters for which the loss is minimum. I will basically see what are the parameters for which the derivative is actually equal to zero, the minima, right? So if you look in terms of a graph, the objective is to find the global minima, right? The minima, the value of the parameters for which the entire model will have very minimum loss. Somebody has sent something. Differentiation, fine. Derivative. Derivative is the core use in neural networks. Please remember, for all those who are interested in deep learning, derivatives is very important. How to find the cost function? How do you define the cost function? Here they have defined a very basic cost function, mean square error. They are going to derive it, and they're going to find, okay, the model will one fine time after 1000 or 2000 iterations will come up and say, boss, now I am ready with this matrix. And you will say, yes, this model now has predicted very close values to this, which means these features are the correct features. Did we generate this feature? No. We started randomly and the model started learning it by gradually learning it. So this is how the model is basically learning the parameters for which the entire model will have very minimum loss. Any issues with the screen sharing?
Yeah, we cannot see your screen anymore.
Yeah, I'll just share it. Is it visible now?
Yeah, it
Yeah.
is.
So this is how actually, we are training our model. For the training part, I have kept it abstract for simplification. As I told, the idea is to develop the interest, not to, burden you with lots of formulas and concepts. Very simple. Matrix multiplication takes place. You calculate a value. We find the error. We go back. We tell the model to adjust the parameters so that one fine day you'll come up with a very correct value, right? That's how the values are actually calculated. Now what happens is, suppose this was initially empty, so and I wanted my model to predict this value. So the model, based on these features, because the model has learned these features, and now model is smart enough to find out, okay, if this user is giving a rating of 1 to this movie, then this user will also give a rating of 1 to this movie, because the parameters are nothing but the context that has been captured, right? The different features which are hidden, the patterns of watching the movie. There are lots of patterns. We cannot just say your location, what type of movie you watch, how many days you watch, which days you watch. All these things are features. But apart from that, there are lots of hidden features also. Okay, so the model is smart enough to find those features also. Right now, we were using 2 features, but there are can be lots of hundred and thousands of features also. So now model is able to basically find out based on these features. One, it has got trained on these features, what are the type of movies basically you're going to like, and what is the review you're getting. So if this person gets a review of 4 for this movie, most likely that this guy is going to like this movie, and hence you'll be getting a recommendation of this movie, right? So as I told in the beginning,
We cannot hear you, Avinash.
Am I audible? I'm really sorry for the technical glitch.
Yeah, you are audible.
Just got a network disconnection.
Okay, no
Okay,
worries.
we are almost towards the end, right? So we were discussing about what are the different types of recommendation that Netflix gives. Netflix not only recommends you the movies, it will also rank the movie, okay, based on the review values that it gets. Also, apart from that, the images that you see, right, they are also being extracted from the videos. So in this movie, there will be some scenes, and based on the interest of the users, right, it will try to find out maybe this is something which is going to trigger the user. Suppose if I am interested in space movies, it knows this user likes something about space. So if in that movie there is something related to space, some image related to space, that's going to gather my attention. Netflix is smart enough, their engine is smart enough, the recommendation engine is smart enough to capture those scenes from the movie and show me in the thumbnail, right? And so that I can basically, immediately fall into the clickbait, and I'll click and I'll just say, okay, I'm going to watch this movie, right? So lots of deep learning and machine learning, data science going on behind the scene. Technology is evolving, the algorithm is evolving, the models are getting more smarter and smarter, right? So I hope you understood how matrix factorization was actually used by the team to solve the Netflix prize competition, and they have actually taken back home a prize money of $1 million. The last slide, as I told, I will be discussing this in the end. So this is the features, right? So this is a user. These are the features. The features can be hidden, right? There are lots of features. The machine has to know itself by training itself, and even the movies has several features. So these are the metrics, and you see, you have to basically predict this. You have this matrix in your data set, and now you have to predict this value. I know what is the value of this because I have the training data set, but I want the model to predict this, and then I'll be comparing the actual value with the predicted value, and I'll see whether the model has been smart enough to fill this matrix with values, which is going to basically give me the exact same matrix, or maybe very close matrix. It will not be exactly same; it will be very close. How do we visualize this problem in terms of matrix? So you have the user vectors, you have item vectors, which is this, right? So this matrix is equal to nothing but the dot product of the two matrices, right? What is the cost function associated with it? You can see this matrix dot product minus the predicted value, right? The predicted matrix, actual matrix. So actual matrix minus predicted matrix, the elements of the matrix, the whole square. This is the cost function. You have to derive it, okay, and you have to do gradient descent. Okay, so for those who are not aware of gradient descent, please refer to the descent articles on net to find out what gradient descent is all about. How does gradient descent actually help us to reduce the loss function, which is the objective, so that we get the parameters which is best to give you the values, and that is what is being used by the recommendation system. Okay, so I think we are towards the end of the session. These are the features, as I was mentioning, that Netflix can use: your watch history, your search history, light videos, what time, device location, language, time of the day. Netflix is evolving. There's a video on YouTube published by Netflix. I would ask you to go through it. How Netflix is actually improving their recommendation system from where they started. Matrix factorization they are trying to improve using more reinforcement learning, deep learning. What are the challenges associated, and why are they still somehow comfortable sometimes to go with traditional approach also? Yes. So, any questions from the audience side? Because I have come towards the end of the discussion. Any questions from the audience? Okay, Camilla likes the thumbnail. Any questions? Waiting for your response. Am I audible?
Yes, you are audible.
Yeah. So seems audience have no questions.
Yeah.
They're comfortable. So I hope you guys enjoyed the session. Please give your review, right? Because on the chat section, at least give you the reviews, whether you enjoyed. What do you think I should have covered more, or what do you think I have covered more, right? So both things are important. Any research paper portal where you can find more details on this, definitely. See, the actual algorithm which is used by Netflix, definitely they're not going to reveal that research paper, right? That is their bread and butter. That is how the competitions work. They are not going to say you how actually we are working it. They can give you a general idea, right? The concepts and the algorithms that you're using it, how they're using it, that is very confidential towards business, right? But yeah, there are lots of research papers. You can definitely Google for them, and you'll find lots of researches going on this. I try to share some research papers on recommendation systems or graph network analysis. Yes, I'll share the book list also and the website also. Maybe I'll mail to someone from Alma Better so that they can forward you.
Surely.
Okay, just put in the chat section like how much did you like the session, right? So I hope you have enjoyed it, because I really love sharing my knowledge, and because I always learn it. It's a two-way approach. The more you enjoy, the more I would learn, and the more I would deliver my sessions, right? So yeah, over to you, Ranjana. Thank you everyone for joining the session and being with me. I hope you are not bored. Right now, you can just take a break and
Yeah.
enjoy your weekend. Yeah.
Thank you so much, Avinash, for this informative presentation on mastering Netflix personalized recommendations and strategies. So I'm sure everyone learned a lot about how Netflix algorithms drive content suggestions and user engagement. We will now be signing off. Thank you so much, everyone, for attending this session.
Just
I
to
hope you
yeah,
have, yeah, you
sorry,
were
just to
saying?
end, I'll share my LinkedIn link
Yes,
also.
yes,
Maybe somebody who's
yes,
interested
please,
to
please.
join the network, they can join, and you can ask any queries you have. Okay, I have a bit busy schedule, but yeah, I always love to contribute in your learnings. So in case any queries, always reach out to me. So I'll just share my LinkedIn profile.
Yeah, you can share over chat.
Yeah,
So
sure.
for any further questions or queries, please feel free to reach out here in the chat session. And we will be sharing a feedback form. Do fill that out, and our team will reach out to you shortly. With us, there will be Manjul Mayank, who will be taking over to this session further. So Manjul Mayank, this is over to you.
Yeah, thank you, Ranjana, and thank you so much, Avinash, for this
Thank you.
wonderful session. I believe I'm audible, right?
Yeah, you're
Yeah,
audible.
you are.
Perfect, perfect. So again, a very important masterclass, I believe, when it comes to the Mang companies part, where we discussed about the Netflix thing and the opportunity that it has for like all of us. Now the question arises from here that if these companies have this much of opportunities waiting for us, how we will go and be a part of these Mang companies or maybe top tech product based companies. The answer is pretty simple. You need a platform. You need guidance from individuals like Avinash, who's currently working in that domain. That means people who are already part of that particular domain will definitely guide you in getting what you want to do, post this skill sets and every other thing. Right now, when I talk about platform, it not only means the topics or the skill sets that you would be taught in that particular maybe duration of course. It's also about the mentorship and the guidance that you get. So there comes Alma Better into the picture, right? So I'm just sharing my screen, and Do let me know if it is visible to all of you. I believe it is visible to all of you, right?
Yeah, it is visible.
Perfect. So why you should go ahead with Alma Better? The first question that definitely comes up in the mind of a learner. But before that, it's important to understand that what Alma Better actually is. So we are a platform where we believe in community formation, where we believe in peer-to-peer learning, right? We always believe that a particular problem can have multiple solutions, and we can reach out to those solutions only by sitting together and discussing about that particular problems. That is why we study in groups, we do projects in team, and we get ourselves ready for the job roles that are available in the market, right? Because you just never know from whom you can learn what, right? So it's important for our community also to keep aspiring and keep helping the new learners who are getting onboarded with us, right? And that is why Alma Better always believes in this particular thing, that we should first of all try to develop that peer-to-peer network communication. That connection needs to be done, because I believe connections can give you a lot more opportunities, going ahead. Now, coming to the question of why I should choose Alma Better. Look, there are like multiple platforms where I can upskill myself. But the reason why you should go ahead and start getting yourself towards Alma Better is that it's important that whatever you're learning should be industry relevant, right? I have seen a lot of YouTube videos that are available over website, which are not any more relevant, right? With the coming up of artificial intelligence, like chat gpt or maybe mid journey, a lot of the topics, they do look bit irrelevant in the industry, right? And you can easily get yourself into this particular industry if you have all those skills that are currently pretty much relevant here, right? So we do ensure that whatever curriculum is being taught to you is relevant, right? And whatever you are learning, you're learning it from basic, right? We do have learners who are from non-tech background or who have not done technical work in their working experience, right? So we do have to ensure that we are teaching everything from basic. So let us assume that if I'm teaching you Python, I should first of all tell you that what Python is and why Python is actually required here, right? So it's important that you should learn things from basic, you go to the intermediate stage, and then you get into the advanced level as well, right? So that is the first point that we try to cater here at Alma Better, that you should get things learned from scratch only. The second thing is obviously live classes. Just like today, Avinash took this master class in the very same way. A lot of our instructors who are working in this very same domain of data, machine learning, and AI, they do come up for like 2.5 hours, and then they do give this live classes, right? Where you can interact with them via chats. You can even get in touch with them via LinkedIn. And obviously, even if you miss out any of the live classes, you will have the recorded lectures as well, where you will revise those things. Even if you miss any of the live classes, you can switch back to the recorded lectures and can learn from there as well, right? Again, the learning part is pretty much important. The theoretical understanding is important, but other than that, it's important that you should practice it. And for that, we have like 1,000+ coding problems and assessments that are there in our course, right? And obviously, if you have a theoretical understanding, you also need to have that practical understanding about that particular topic. And for that, we have like 20+ capstone projects, right? Where you will be applying all those skills, all those topics that you have learned or what you have covered, right? We have like daily doubt resolution sessions. So this is one of the most important criteria that we try to cater, right? Let us assume that you're watching any of the recorded lectures and you come up with any of the doubts. You can directly go to our live doubt resolution portal and you can get your doubts sorted there only from the subject matter experts that we have here, right? So you have like real time doubt resolution feature out here, which definitely helps all those, right, who have missed any of the live classes, or they are purely dependent upon watching only the recorded lectures because obviously of their work timings or any other reason. Other than that, we also have like 1:1 mentorship sessions, right? And all these mentorship sessions are from the industry experts only who are currently working in that industry, because what I believe is that theoretical understanding is okay, practical understanding is also good, practicing all those things is super good, but you should have a guidance, because in this data domain there are like multiple job roles that are waiting for all of you. So it's important that you should have this understanding that which particular job role will suit me in my upcoming career. And for that, it's important that you should have these mentorship sessions, because you learn a lot of things. All these mentors, they are industry experts only, so they help you understanding how things are going on in this particular industry. Obviously, when the learning phase is over, everyone they do get excited about the placement thing, and for that we do ensure that we are covering everything, whether it's the mock interviews, your resume building, uh, having a few of the guest lectures that are completely based upon the kind of questions that could be asked in any of the interviews. You will get a dedicated career coach. Again, career coach is someone who is already working in this industry, and he will help you in understanding about the number of rounds that could be taken in that particular company in which you're applying. So obviously we cover a lot of things in the placement criteria, as well the placement cell that we have out here at Alma Better. And again, with like 700 plus hiring partners that are ranging from the product-based companies to the service-based companies to the startups, we do assure that it's 100% job guarantee program for all of you, right? So this was about why Alma Better. And again, what are the learning activities that you will be doing? You will be having your live lectures, your recorded classes, your projects, your assignments. You will have your group discussions, which I believe is a very important part if you're learning something. Guest lectures, just like Avinash took one of the lectures today, it was just kind of a guest lecture. So you will get more and more, guest lectures like this, so that you can get the exposure of how data industry is actually working today. Mentorship session, guidance, that is very much important. And obviously for the practice thing, you have like capstone projects and competency challenge. We do have these things because we want to track what you're doing, how you're doing it, and if you are lagging somewhere, we can just help you out in getting something best out of it. Okay, so this is again very important. The companies that we have from here, it can range up to a huge top tech company like Amazon, to a startup, maybe Mintra. We can have companies from consultancy firms, that is PwC. Then we have a company, from the crypto world as well, that is Polygon. Then we have finance companies like JP Morgan Chase. And again, a few of the IT services companies are also there. For example, we have Cognizant, we have Capgemini. So, data has its value in all these fields, whether it is e-commerce, whether it is pharmaceutical companies, whether it is finance company, whether it is IT services, right? Whether it is consultancy firm. So you can see one thing, that if you are very good in handling data, there are like multiple, I would say, options that are up for you, right? You can just, even if you're working in any of the finance companies, you have this opportunity of getting in finance company only, but obviously in the form of data, uh, as already been mentioning right through this particular presentation. Even if you're from a banking industry, you do not need to switch it and get into the IT services. If you're doing it in the data domain, you can even switch in the very same banking company as well. So this is the biggest, I would say, benefit that data provides, that it has its reach in every sector that is currently there in the IT field. This is very, again, interesting thing that I do share in these master classes. We do promise a placement guarantee of 5 lakhs per annum. Initially, we will train you for like 6 months, and post that we will start your placement services and your resume preparation and every other thing. But most of our freshers, like 19% of our freshers to be more precise, they do get a package of 5 to 7 lakhs per annum, right? And we do promise that you will not be getting anything less than 5, right? So that 5 to 7 is there, that is 19%. Now, something which is highly encouraging for all of you, and this salary distribution is for the freshers, right? They don't have any prior background of IT. They don't have any prior background of graduation in tech. If you see, like 29% of the people, they're ranging in between 7 to 8 lakhs per annum, and 37% are in the range of 8 to 9 lakhs per annum. That means in between 7 to 9, we have like more than 50% of our learners, not only more than 50, approximately 70% of the learners are falling in this category, which is a very good thing. If you're a fresher and if you want to get into this data domain and you get a package of like 9 lakhs per annum, it's a very big deal, right? You will get a very good kickstart in your career. Now, what is even more inciting is the fact that there are like 15% of the people who have got the package of more than 9 lakhs per annum, right? So if you're dedicated, if you're working hard, if you're getting right set of guidance, you might end up even getting a package that is 11 or 12 lakhs per annum as well, because 3% of our learners do end up getting more than 10 lakhs per annum. That means that they start earning around a lakh rupees monthly, right? Even if they don't have any prior background of any of the IT thing, which in itself is a huge thing for that particular learner. It's all about the amount of dedication he has shown in those 6 months, right? So again, it's kind of a salary distribution that only excites our learner, and also, you know, encourages us to work more in getting you guys a placement that is obviously above what we have promised, right? Some of our instructors like Avinash, you know, he's also someone who is currently working in the top tech company, just like Rochit is there, who is working in BCG. It's a consultancy firm. We have Sayan Day, who is currently, you know, working as a data scientist in Walmart. So we have the instructors basically who are working in this industry only, like Jyotirmay Dev, he's currently in Apple. Neeraj Sharma is working in Microsoft. So we do have companies from top, we do have instructors from top tech companies, right? And they give you that exposure that you want. That is why we don't believe in getting any of the professors or teachers with us, because we believe that you can get that kind of exposure, you can get that kind of understanding from them only who are working on those tools, right? Today, when Avinash was talking about how Netflix is working basically in terms of ML and things, it's pretty important that you should understand the way his company is actually using all those tools, right? Theoretical understanding is not tough, but understanding how that theory is being utilized in top tech companies becomes pretty much important once you're looking forward for these companies, right? That is why I told you initially that we try to ensure that most of the things that are being covered in this particular Alma Better 6 months of program is industry relevant. There is no point giving out your time to all those topics that are not currently relevant. So these are some of the instructors that we have. We do have instructors from the man companies, then we have someone from the product based companies, some of them are from service based companies, but we do ensure that most of the instructors are working professionals who are dealing in this domain only. Some of the success stories, again, these people, even if you visit our website almabetter.com, you will get to know that how these people who were from a different domain, or who were from a very different background, they got themselves transitioned into this data domain. It can be data analyst, it can be a business analyst, it can be a senior consultant technology may. So you can just visit their LinkedIn profile and can check uh, how this transition took place and what was the background they had before getting this transition. All right, so anything that anyone wants to ask till now about the admission process, or anything regarding Alma Better? All right, so again, I'm sharing my screen and giving you a quick walkthrough of our dashboard, how it looks like. So this is how the website basically looks like. Once you type in almabetter.com, you will land up here, right? Then we have our courses. We deal in the certification courses, then we deal in master's courses also, and we deal in UG diploma courses as well, right? So this is what the first look looks like here for Alma Better. It's a certification in full stack data science and AI that we are giving. We have added AI, artificial intelligence, because I believe in the next 3-4 years AI things in this industry. We have a batch that is starting from 5th of September. That is the upcoming Tuesday. So if you guys are interested for this, perfect. We can you can even coordinate with our counselors, or you can directly visit the website and can enroll yourself. This is a 6 months part-time program that we have that consists of live online classes as well as the recorded ones as well. We have a curriculum that again we have redesigned. The reason being a lot of chat GPT tools and other AI tools that have come into the market. And the best part is that a learner should not be having any prior coding experience required. So even if you're coming from a very different background, need not to worry. We are here to take care of that as well. We have like 700 plus hiring partners already being witnessed. We have an average salary that ranges in between 8 to 12, right? With the highest being 25. We have instructors, as already being discussed, from top tech companies, and these are some of the reviews of our students as well. So if you look, Somajit Das, he was a fresher in mechanical background and he got into business analyst. Same goes for Pradhan as well. He was a fresher, got into data analyst. Soumya Jan, well, she was in this domain only, but she got a promotion and she got a hike as well in paisabazaar.com. So even if you are from, even if you're not from a domain of data, you end up getting the opportunities, and if you are from that domain, you end up getting hike as well as the opportunity, right? So it works for both the sector of audience that we have here. So this is how the foundation track works. Like, we have like 6 months of foundation track with us, where we have uh, Python that we teach in the initial month. Then again, we get into the numerical programming of Python for 1 more month. We get covered the SQL part, right, for 1 month. Then we have some of the tools like MS Excel, Power BI, and Tableau for 1 more month. Then we get into statistics and the mathematics part that we have here. And then we end this entire 6 months of course by telling you about the machine learning. Now, the best part about this particular syllabus is that in every topic you will get to know about how ChatGPT can be helpful in learning this particular topic, or any other AI tool, how it can make things easier for you, right? And that is what we focus on here at Alma Better, that if anything is updated in the industry, we do ensure that it is covered in our particular syllabus, right? So this is the 6 months of foundation track that a learner has to go through. Then obviously we get into the Alma X career track. Alma X is basically the placement cell that we have out here. So what we do here is that we start with business communication. Obviously, we will help you building your resume. We'll also help you in email writing and every other thing that is required to be prepared for the interviews. And obviously, then you will have your mock interviews and in many other things that will be covered up here at Alma Better in this placement cell that we have here. Again, coding and technical revision is pretty much important. Even if you're giving your interviews, it's very good that if you're practicing your topics and the syllabus, and we do ensure you're doing it, we just keep on giving you more and more problems, because practice always makes a person perfect, right? And coding is most like mathematics. The more you practice, the more easier it gets. These are the things that are already being discussed: the resume building part, the placement support part, the mock interview part, the dedicated career coach part. These are the companies that are with us, right? It ranges from product based companies to the service based companies. We have like only 9 slots left for the upcoming batch that is starting from Tuesday. The batch is cohort Chandrayaan, and you directly can go there and enroll yourself. Again, the instructors, I already have covered this. And let me just, there are certain projects also that you will be doing, right? And the projects will be from Netflix, they could be from Zomato, they could be from Airbnb, Yes Bank. So we do ensure whatever project you are doing, they're also pretty much industry relevant and give you the exposure of the topics that you have learned in the theoretical aspect. All right, so you can just directly go to the website and can scroll down, and you will get a lot of information here only. Now, this is the unpaid version of the dashboard that what it looks like, right? Now, this is again the paid dashboard part that we have here at Alma Better, right? So I was basically enrolled in cohort Paris. So this particular topic will be told to me on 5th of September. So you can check your upcoming live classes here as well. Other than that, you will also understand about the topics that you have already covered, or the topics that has already been covered in this particular cohort or batch. So currently we are on object-oriented programming, and rest of the things are already been covered. So you can have a track over this from here. You can go to the classroom section here, and it gives you a schedule of upcoming classes that will be happening. Like the next class for this particular cohort is on 6th of September. And even once the classes are done, you will also get the recordings of the classes. So you just have to click on this and you will end up getting the recording of this particular live class. Other than that, if there are any notes that are being shared during this particular class, we also do attach it here, just like this view handouts. So you can download these notes and can use it post the live classes or post the recording classes to revise the things, to revise the concepts. And obviously the thing that I was talking about is the practice part, where we have like coding problems, coding assessments, quiz assessments. There are more than 500 coding problems that we have out here. Coding assessments, again, it's like more than 500 that we have here, and same goes for quiz assessments as well. So every assessment will come up with certain number of questions that you have to do. Just like this particular assessment consists of 70 questions that you have to attempt in 120 minutes. So we do ensure that your practice part is also going right here. Projects, as already been mentioned, we have like 20 plus projects, and you have to do 4 projects out of them. That is pretty much compulsory, right? And this product, these projects are also from different sectors. Like this is from the hotel industry. Most probably this project is from Airbnb. Then we have a project on EDA, that is Play Store application. Then we have a project from finance, that is World Bank Global Education Analysis. Then we have global terrorism data set. So there are like multiple industries from where you get to cover your projects, right? And from here on, you can book your mentorship session, right? So you just have to click on book now here. You have to go on mentorship, click on book now, and you can choose any of these topics for mentorship. Let's assume that you are facing any difficulty in doing any of your projects. Just book one of the sessions for project guidance, select your date and time preference, book here, and that session will be booked to you. You have to do it in 1 week prior so that we can also check the availability of the mentors at that point of time. Now, if you look at the bottommost right of this dashboard, you will have this help section. So report a problem. It's the way where you can directly go there and can write your problem and paste it. The subject matter expert will get in touch with you and solve it out. Then you have like live support, right? So what happens here is that, as I was mentioning, that you have like daily doubt resolution sessions that are happening, right? So if you're watching any of the recorded videos, and if you feel like that you are facing any difficulty, you can directly go to this live support. Our subject matter experts are there only from Monday to Saturday, 10:30 to 7:30. They're here. You can just grab any of the tables, right? You can sit here and can, clarify your doubts in real time only, right? So again, even if you miss out any of the live lectures, or you're facing any difficulty in doing any of the projects, assignments, or any topics, you can directly go there and clarify your doubts as well. So that was that from the part of dashboard. Nothing much to cover here. So if anyone has any questions regarding this, we can have that. Else, it's a wrap from my end. Ranjana, I think you can take this
Yeah.
ahead here. There are not many
Thank you
questions
so
coming
much.
up.
Yeah, thank you so much, Manjul. So we are ready to sign off from this session. Again, if you guys have any questions or any queries, you can feel free to reach out to us. You can even drop your queries over the chat box right now. And will there be any feedback from Manjul from our end?
Yes, I think you must have received one, so you can share it here only, the feedback form, and the learners can fill it.
Okay. I guess I don't have received any feedback from. If it is fine, can you share?
Let me check. But before that, all those who attended this particular session for the next 24 hours, we will be providing you a discount coupon code that will be of 15% over the current price that we're giving it to you for the course. The current price is 29,999. But if you're using it in the next 24 hours, you end up getting 15% discount as well. The coupon code has been shared here only. That is learn15. That is applicable for next 24 hours. Just give me like 30 seconds.
Okay.
Cool. I think that was that. Have confirmed this with the team as well. So that was that for
Hmm.
this session. No feedback form here for the learners now, but you guys can use this coupon code to enroll yourself in the upcoming batch that is starting from Tuesday. Thank you so much, Avinash, for your time and for this informatory session. It was really exciting for all of us, and we learned a lot from this. Thank you so much, Ranjana, for coordinating this entire masterclass so well. We do come up with all these master classes every weekend, basically on Saturday. So all the learners who were part of this master classes, if you have your friends, family members whom you think are aspiring to get into this data domain, you can bring them up here as well in these particular sessions. Okay, so that was that from my end. Enjoy your weekend, guys. Thank you so much. Bye bye.
Thank you, team. Thank you.
Thank you. Bye.